Let's start with this mini crash course, which is on acid-base salts, and we'll be specifically discussing preparation of salts. So now the first thing is, what's an acid? Acid is a proton donor. Basically, it produces H plus one ions when it's in aqueous state. So next time when you think of an acid, think of a molecule. It could be any molecule that is giving off H plus one ions. So it increases the amount of H plus one ions whenever there's an acid that's present. The next one, what's a base? A base is a proton acceptor. A proton, remember, is H plus one ion is known as a proton because its electronic configuration, it only has one proton. So what's a base? It is accepting H plus one ions when it's in aqueous state, or vice versa. There's another definition of a base that it produces OH ions. So simple definition: if they ask you, acid is a proton donor, base is a proton acceptor. So I've made a diagram as well. This is what a base would look like. It is a molecule. I'm going to describe the molecule later on. So it's going to be accepting or removing H plus ions from the environment. Now, the next thing that we're going to discuss is the importance of acids, bases, and I'm going to introduce the pH scale as well. Now, before moving to the importance of acids and bases, the thing that they're related to is water. Water is what's important. Water is the ultimate chemical. That's everything. All chemistry on planet Earth revolves around water. 70% of the Earth's crust, Earth's surface is water. 50 to 80% of all life forms, for example, humans, their 50 to 80% mass is just water. We are mostly water. So basically, why is water important? Because water is your main solvent. So it's our main solvent or medium for reactions. Now, how does water really help? Because without water, particles would not be able to move around. The reason there's no chemistry happening on the moon is that if there is particle A somewhere on the moon and there's particle B somewhere else on the moon, they're going to stay there forever because they can't move. Water on planet Earth helps to move things around. So if particle A and particle B are floating around in water, particle A and B would eventually meet and they would collide and they would either share electrons, one would lose electrons, the other one would gain electrons. Some sort of chemical reaction might occur when this happens. But for any chemical reaction to happen, the particles must be able to meet in the first place. So water helps that. So here you can see a couple of diagrams just to show you the importance of water. So blood takes all your particles and distributes them. The glucose that you eat, the proteins that you eat, they're broken down into amino acids. And your artery system, it's basically just water. Blood is basically just water. And your heart is basically like a water pump that is pumping water throughout your system. And the water is carrying all those particles. And those particles are able to reach the desired places because water is able to get there. Same with plants. How do plants absorb minerals? They absorb water from the roots and the water evaporates from the leaves. So there is constant water transportation that's happening and the water carries all the particles that the plant need. As soon as you stop giving it water, the particles would not be able to reach the cells in the leaves, in the stems, and the plant would not be able to grow and it's eventually going to die. Now let's come straight to the point. So how does water link with acids and bases? So you've got water over here. Remember, all reactions, most of the reactions on the planet Earth are happening in water. The particles are floating around in water. So water is basically a lot of H2O molecules all bumping into each other, slipping and sliding past each other. So while they are moving around, so for example, there's this water molecule, and that water molecule is slipping and sliding and moving and colliding with the container and with other particles. So what happens is some of the water molecules would eventually break down and they would produce two ions. One of them is going to be an H plus one ion and the other one is going to be an OH ion, which is a hydroxide ion. So you've got the hydrogen ion and you've got the hydroxide ion. So some of the water molecules over here, because of the constant bumping and collisions with the container and with each other, some of them might dissociate. Very few, not all of them, but some will dissociate. So here, as you can see, I've dissociated another water molecule. So there's some H plus one and some OH ions that would be part of the solution of the liquid water that you have. Now, this kind of water where the quantity of H plus one and OH ions, because the water molecules they're split in equal parts, the amount of H plus one ions that are going to be produced and the amount of OH ions that are going to be produced are going to be equal. And if they are equal, that is known as a neutral solution. That is known as pH. You call it pH, and you say that the pH is equal to 7. That's a mathematical expression which is not required at the moment, but what you should know at the moment is what does pH mean? pH 7 means that the amount of H plus 1 and the amount of OH ions are equal in quantity, and this is known as a neutral solution. Now, what if in this neutral solution, you decide to add an acid? Remember our definition. What is an acid? It's a proton donor. It produces H plus ions. So all of a sudden, if you add a molecule that is constantly producing, so imagine this molecule inside this water and it's constantly producing H plus ions, the quantity of H plus ions in your solution would start to go up. There's going to be more and more H plus 1 ions in your solution. And that is known as an acidic solution, because now what has happened is, that the H plus ions are now, you've got a lot more H plus ions in solution. Like if you even count in this diagram, there's 1, 2, 3, 4, 5, 6 H plus ions, and there are just 2 OH ions. So the amount of H plus ions are a lot greater compared to the OH ions. That's known as the solution being acidic. And in terms of pH, that's pH less than 7. Whenever your solution is acidic, the pH is going to be less than 7. Vice versa, what if you decide to add a base? Now, as soon as you add a base, what does a base do? It's a proton acceptor. It removes H plus 1 ions from the solution. That was the definition. So as soon as you add a base, the amount of H plus ions is going to decrease. And remember, the definition of a base was also that it increases the concentration of OH ions. It produces OH ions. So the quantity of OH ions are going to go up when you add a base. So as soon as you add a base, the base removes all the H plus ions and increases the amount of OH ions. So this kind of solution is known as a basic solution, where the amount of OH ions are a lot more compared to the amount of H plus 1 ions. So this is so whenever the OH ions go up and the H plus 1 go down, that's your basic solution. Your water has turned basic, and that in terms of pH is going to be called greater than 7. So whenever you look at water, there would be 3 types of water. Either the water is going to have equal amounts of H plus 1 and OH ions, that's going to be called a neutral solution, that's going to be called pH 7, or it's going to be acidic. That means the amount of H plus 1 ions are a lot more compared to the amount of OH ions. Why? Because you've added something that's an acid, and the acid increases the H plus 1 ions. Or you would have a basic solution. A basic solution is when you have less H plus 1 and more OH ions, because the base removes H plus 1 ions and increases OH ions. That's going to be called basic, and the pH is going to be greater than 7. Now, here in front of us, I've also drawn a pH scale. So pH 7 is your neutral part. That's water being neutral. pH, the closer or further away you are towards 14, that would mean you're strongly basic. That means the OH ions are a lot more compared to the amount of H plus ions. And you're going to be strongly acidic the further you're down below. If it's closer to 0, that means you're strongly acidic. And that means the amount of H plus 1 ions are a lot more compared to the amount of OH ions. But also, the closer you are to 7, for example, if you're slightly higher, 8 to 9, that's going to be called weakly basic. You are basic, but it's not an extreme condition. The OH ions are greater compared to H plus 1, but not that much. And if you're closer to 7, but slightly lower than 7, like 5 and 6, you're going to be called weakly acidic. That means that the H plus 1 are higher, but not too high. So try and keep these basics in your head: neutral, equal, H plus 1 OH ions, basic, and acidic. Now, the reason why this pH scale is important is because every reaction on planet Earth is happening in water. That's the first thing. And the type of water that you have, whether it's neutral, basic, or acidic, that will affect the reactions. Every reaction has a particular pH preference. Some reactions, they need more H plus ions, so they're going to perform better if there are more H plus ions. That means they would perform better if the water is strongly acidic or slightly acidic, because they need more H plus ions for the reactions to happen. Some reactions need more OH ions, otherwise they won't happen. So if a reaction needs OH ions, they're going to perform better at higher pH, where there are more OH ions in water. And then there are some reactions that might need both H plus 1 and OH ions, so they're going to perform better if the pH is close to 7, where there's equal amount of H plus 1 and OH ions. So here are some real world examples of products that are acidic, or places where there are acids and bases, which are pretty much everywhere, because everywhere there is water, so the water is going to have a particular pH. So acids, stomach, strongly acidic. All your digestive reactions that are happening in your stomach, they need a lot of H plus ions, which is why they happen at a very low pH, which is close to 1. Lemons, they've got citric acid. Lemons and oranges, anything, all your citrus fruits, they have citric acid, which is why they taste sour and bitter. So they are also strongly acidic. A lot of your fruits, tomatoes, bananas, etc., they all have some acids in them. So they've got molecules that are proton donors that produce H plus ions. Milk is very slightly acidic as well. Pure water is neutral, which we have discussed earlier. Then you've got basic products. Eggs are slightly basic, weakly basics. 8 is weakly basic. You've got baking soda. Soaps are basic. And ammonia is basic. Bleach, oven cleaners, strongly basic. Now, here are some general properties of acids and bases. Acids, all acidic products, like lemons, etc., they taste very sour and bitter, and they react with metals to give off hydrogen gas. So they all pretty much not with unreactive metals, but mostly with metals they react. They're good electrical conductors as well. Bases, they taste bitter. They feel slippery. I mean, soaps are basically bases, and they dissolve fats and oils as well. So these are some general properties of acids and bases. Now what we're going to do is we're going to move towards the more difficult part, which is formulas and equations of acids and bases. So we're now going to start with formulas and equations, and we're going to learn about all the equations related to acids, bases, and salts. And the first thing is we're going to talk about the formulas. Now, the very basic is we need to remember the charges on different ions. Now, if you remember ionic compounds were made between metals and non-metals, where the metals, they always like to lose electrons and they would turn into positive ions. And you had your non-metals, they would always gain electrons and they would turn into negative ions. So ionic compounds were a positive ion attached to a negative ion. And your ionic compound would form ionic lattices. This was known as a giant ionic lattice, which was a regular arrangement of positive ions attached to negative ions. Positive ions and negative ions would all attract each other. So the metal would lose electrons and the non-metal would gain electrons. A positive ion will get attracted to a negative ion, and a giant ionic lattice is going to be formed. So what was needed was that you should memorize or remember that if you have a group 1 metal, its charge as an ion is always +1. If you have a group 2 metal, its charge as an ion is always going to be +2. Transition metals, which are the ones that appear in between group 2 and group 3, they always have variable charges or variable oxidation states. For example, iron could be +2, it could also be +3, it could even be +6 as well. So for these, the charges would be written in the formula because you can't really tell what the charge on iron or copper is going to be. Then you have group 3, which are also mostly metals, so they have a charge of +3. Group 4 can be +4, -4, and then you have your non-metals on the right side. They're going to form negative ions. Group 5 will have a charge of -3, group 6 will have a charge of -2, group 7 will have a charge of -1, and group 8 is your noble gas, so they have complete outer shells, they don't lose or gain electrons. So here are some very basic formulas. Na belongs to group 1. It's a group 1 metal. So it's going to lose electrons. It's going to form a +1 ion. And chlorine is in group 7. So group 7 has a -1 charge. So Cl has a -1 charge. It gains 1 electron. So Na loses 1 electron and that 1 electron is gained by Cl. It becomes +1. This one becomes -1. So the formula of Na and if Cl combined, it's going to be NaCl. That's it. You have 1 Na, you have got 1 Cl, and it's going to be called sodium chloride. And make sure you get the naming right as well. It's a sodium ion and a chlorine ion. A chlorine ion, the negative ion, its name slightly changes. The end part of the name, the suffix, changes to IDE. So if it's chlorine, it's going to become chloride. So remember that. If it's phosphorus, it's going to become phosphide. If bromine forms a negative ion, it's going to become bromide. If sulfur forms a negative ion, it's going to become sulfide. Now, here's another one, example B, that's magnesium, that's group 2, so it has a charge of +2. Oxygen, which is in group 6, it has a charge of -2. So magnesium loses 2 electrons, oxygen gains 2 electrons, that's it. So there's one magnesium, there's one oxygen, that's the formula, magnesium oxide. And it was magnesium ion and oxygen ion, but remember the negative ion, the name ends with "ide." So instead of calling it oxygen, you're going to call it oxide. So remember, what does IDE represent? All negative ions in the periodic table, they're going to be called with their suffix would change. Now, these formulas were simple, that the amount of electrons lost and the amount of electrons gained are equal. So magnesium loses 2 electrons, oxygen gains 2 electrons. Another thing about ionic compounds and the formulas is that the formula represents the simplest ratio in which the ions are going to exist. For example, NaCl, it's not going to be just one Na and one Cl ion, because the NaCl lattice is going to have billions of sodium ions and billions of chloride ions. They're all attracted to each other. and Na plus 1 will attract Cl minus 1, Cl minus 1 will attract another Na plus 1, the Na plus 1 will attract another Cl minus 1, and it just goes on and on. It's a giant structure. So the formula represents the ratio in which they're going to exist. For every one Na, there's going to be one Cl. Whenever Na loses one electron, another Cl gains one electron. So it tells you the ratio in which the ions are going to be present in the ionic lattice. Now, things become more complicated when the amount of electrons lost and gained are no longer equal. So here's an example, 3 examples actually. I'm going to start with the first one. So aluminium, metal, and fluorine is a non-metal. Aluminium is group 3, fluorine is group 7. So according to the chart over there, that's aluminium would be plus 3, fluorine would be minus 1. Now, aluminium plus 3 and fluorine being minus 1. What does that mean? So what it represents is that aluminium plus 3 means that it's losing 3 electrons. But fluorine, on the other hand, is minus 1. It's in group 7. It is capable of only gaining 1 electron. So where do the electrons go if aluminium is losing 3 electrons but fluorine is only getting 1? So how in the ionic lattice are the electrons, how do you make the electrons equal? So the simple method is the criss-cross method, which is that you just get the 3 over here and the 1 on this side. So there's going to be Al would be, if it's minus 1 written over here, you're going to call Al would become 1. And if fluorine, if there's plus 3 written over here, you're going to make fluorine 3. That just means that for every 1 Al, there's going to be 3 fluorines. Why 3 fluorines? So because if you have 3 fluorines, then the amount of electrons gained and lost is going to become equal. Because aluminium is losing 3 electrons. Fluorine is only gaining 1 electron. So if you have 3 of them, in total, they're going to gain 3 electrons. So if you have 3 fluorines, all 3 independently, there's 1 Al, and there's going to be 3 fluorines. So something like this, aluminium losing 3 electrons, fluorine only gaining 1 electron. So there's going to be 3 of them. But you don't have to go into this much detail. All you need to do is, you see the 3 over here, you multiply fluorine with 3. You see the 1 over here, you multiply aluminium with 1. So there's 1 Al and there's 3 fluorines. There's no need to write 1 because even if you don't write it, it's still 1. Same applies to our second example, which is sodium oxide. So sodium is in group, it's in group 1. So sodium is plus 1. Oxygen is a non-metal, it's in group 6, so it is a minus 2 ion. So oxygen is minus 2. Don't think about it. Sodium is losing 1 electron. Oxygen, on the other hand, is gaining 2 electrons, but you don't need to think about that. The simple hack or shortcut is just put the 2 over here and the 1 on this side. So there's going to be 2 sodiums and there's going to be 1 oxygen. So the formula of sodium oxide, remember it was sodium and oxygen ion, but the name at the end is going to change. It's going to be called sodium oxide. The other example is also very similar. Calcium is plus 2. It's in group 2. Nitrogen is in group 5. What is the charge in group 5? You can see over here it's minus 3. So nitrogen is minus 3. So calcium is plus 2, nitrogen is minus 3. You do crisscross, get the 3 over here, get the 2 over here. So there would be 3 calciums and there are going to be 2 nitrogens. And so that's the ratio in which the ions are going to exist in the ionic lattice. And the ratio always has to be the simplest ratio. If 3:2 is the simplest ratio, but in some cases, the ratio can be further simplified. So always make sure that you keep the ratio in the simplest form, which in 99% cases is always going to be in the simplest form. So this over here is your calcium nitride. It was nitrogen ion, but now it's going to be called nitride. Now, the next thing that we're going to talk about are polyatomic ions. These ions are molecules that basically end up gaining or losing electrons. So you've got your hydroxide ions, which is OH minus 1, sulfate, SO4. We're going to come back to that, but let me just first explain to you very quickly what a polyatomic ion is. So molecules ending up gaining or losing electrons. So let's, I'm going to give you an example of a hydroxide ion. Like how is that ion really formed? So here I have an oxygen atom. Oxygen is in group 6. It has 6 electrons in its outer shell. It's a non-metal. Non-metals, they try to gain electrons and they try to complete the outer shell. So it needs 2 electrons. So what I'm going to do is I'm going to draw a hydrogen atom next to it. Now, as you can see, I've drawn 2 hydrogen atoms. Oxygen needs 2 electrons. So it's going to try and attract those 2 electrons from the hydrogen atoms. So here you can see that the hydrogen atom electrons, it's also a non-metal, so non-metals, they never lose electrons. So the hydrogen atom takes its electrons and goes to oxygen and starts sharing electrons. Oxygen is going to attract or pull that electron from hydrogen. So oxygen has now managed to gain 1 electron. but it's sharing electrons. Non-metals, they always share electrons because they're never willing to lose electrons. Oxygen over here needs another electron because its outer shell now has 7 electrons. It still needs 1 electron. So it sees the hydrogen's electrons, and the hydrogen atom gets pulled towards this oxygen. And that's how a water molecule gets formed. A neutral water molecule gets formed. Oxygen has managed to get its 2 electrons, and it's sharing electrons with hydrogen. It has pulled electrons from hydrogen, and non-metals never lose electrons, which is why they end up sharing electrons. But what if there was no other hydrogen atom? Uh, so what has now happened is that oxygen over here it still needs it still needs 1 electron. So what if there is no hydrogen next door? And instead you had a metal, you had a sodium atom. And remember, what do metals like to do? They always like to lose electrons. So sodium atom would want to lose electrons. Oxygen needs 1 electron. So what will happen is that this 1 electron is going to be pulled by this oxygen atom. The metal would end up losing electrons, and the sodium will now get a charge of, so it will get a +1 charge, while this molecule over here, oxygen was trying to complete its electrons. It has gotten that 1 extra electron. So it's got an extra electron. So which is why this molecule over here is going to end up getting a -1 charge. And that's how a hydroxide ion is formed. So this is your OH -1 ion. It was a molecule which basically ended up gaining an electron, and therefore it became a negative ion. So you don't need to go into this detail. What you need to know is, and you need to know this by heart, no one is going to ask you about the detailed electronic structure of these polyatomic ions. You just need to have a sense of how these polyatomic ions are formed. But what you need to know is you need to remember all of these by heart. So whenever from now on, this is super important in chemistry. It's one of the most important things. So there's a note written, memorize this. So whenever you hear the term hydroxide, that's OH -1 ion. And it is one thing. This hydroxide ion is one thing. It's an ion. It's a combination of different atoms joined together, but they turned into an ion because they ended up gaining electrons or sometimes losing electrons to other elements. Sulfate is SO4-2, carbonate is CO3-2, nitrate is NO3, it has a charge of -1. Phosphate is PO4, it has a charge of -3. Ammonium is NH4 +1. Sulfide is SO3 with a charge of -T. -2. Phosphide, never confuse your sulfides with your sulfates, your nitrites with your nitrates. Nitrite is NO2 -1. You've got your hydrogen carbonate, which is also known as a bicarbonate. You've got hydrogen sulfate, you've got dichromate 6, magnate 7, MnO4 -1, chlorate 5, chlorate 1. So you have to remember all of these ions by heart. Plus the previous stuff that we had already discussed, that you have to know that group 1 is +1, group 2 is +2, group 3 is +3, 4, 5, 6. You need to know the charges on the ions in your periodic table. And always differentiate between ides. Ide is, remember, just the element in the periodic table forming a negative ion. So always differentiate between nitride. Nitride would just be nitrogen, which is in group 5. It will have a charge of -3. So always differentiate between nitride and what's ending with an 8. When it's ending with an 8 or an ite with a T, then that's nitrogen combined with oxygen. That's the ion. Nitrite would be NO2 -1. But when it's IDE, then it's just nitrogen. If it's carbide, it's just carbon. If it's sulfide with a D, then it's just sulfur. With a T, it's going to be combined with oxygens. So these are the ions that you just have to memorize. So we're going to do some questions, crisscross questions related to this. So what I'm going to do is I'm going to write down the formula of calcium nitrate. What I'm going to do is calcium. I already know what calcium is. Calcium is group 2. So group 2 will have a charge of +2. What is nitrate? Nitrate, remember with a T, that's this one. Where is nitrate? Nitrate is NO3 and it has a charge of -1. Remember, this thing is one thing. You can't change the formula of a nitrate. You can't make it NO4. It always is going to be NO3 and it will always have a charge of -1. So nitrate is what? It's NO3 and it's got a charge of -1. So what is going to be the formula? We're going to do crisscross. If I do crisscross, then calcium would be 1. There's going to be 1 calcium and 2 over here. Nitrates would be twice. So calcium would be just 1. You don't need to write that. 1 is understood that it is 1. And nitrate, remember NO3, you have to put the whole thing in brackets. NO3 will be twice. So that's the formula of calcium nitrate. So quickly, let's try and do another one, magnesium phosphate. So what's magnesium? Magnesium is Mg and it's in group 2, which is +2 as well. Phosphate, again, with a T. Phosphate is what? Also, don't confuse phosphite with phosphate. Phosphate is PO4 and it has a charge of -3. So that's what phosphate is. So phosphate is PO4 and it's got a charge of -3. So if I write down the formula, if I do crisscross, magnesium would be thrice and phosphate would be twice. So there's going to be magnesium would be thrice and your phosphate would be twice. So that's the formula of a magnesium phosphate. Now let's do another one, which is aluminium phosphide. So aluminium is group 3 in the periodic table. So aluminium would be +3. And remember, this is IDE. So it's not with oxygen. It's just phosphorus. It's just phosphorus, which is in group 5. Phosphorus has the symbol P. And group 5 means that it's going to have a charge of -3. So remember, when it's IDE, it's just the element. So what is the formula if I do crisscross? It's going to be, I'm going to have 3 L's and 3 P's. If I do crisscross, it's going to be 3, 3. But remember this, that the ratio of the ions, the formula tells you the ratio of the ions in the ionic lattice, and it always has to be the simplest ratio. So in this case, if it's a 3, 3 ratio, that ratio can be further simplified, and you're gonna get a 1, 1 ratio. Or you can just make sure that whenever the charges are equal, the number of electrons lost and gain are equal. So you don't have to do anything. So it's just going to be 1, 1 ratio, that's it. So here are some more examples which I've already done. Remember, for transition metals, the charges would be written in the formula. For example, if it says iron 2, that just means Fe is +2, nitrate is NO3 -1. You do crisscross, there's going to be 1 Fe and there's going to be 2 nitrates. So NO3 bracket twice. Sodium sulfide, similarly, sodium is in group 1, so it's +1. Sulfide is SO3 -2, which is written above. Do crisscross, there's going to be 2 sodiums and there's going to be 1 sulfide. So 2 sodiums and there's 1 sulfide. You don't write 1. Potassium phosphide, potassium K, that's group 1, so +1. Phosphide is PO3 -3. If you do crisscross, it's going to be K3, PO3, and so on. Sodium sulfide, IDE, that just means sulfur, that's it, which is group 6, so it's -2, N is +1. You do crisscross, it's going to be Na2S. Barium hydroxide, barium group 2, +2. Hydroxide is OH -1. Do crisscross, 1 barium and 2 hydroxide, so BaOH twice. Aluminium carbonate, aluminium group 3, +3. Carbonate is -2. Do crisscross, 2 aluminiums, 3 carbonates, and that's it. So now we've done basic formulas. What we're going to do is we're going to try and move towards the formula of acids. So acids were proton donors. So they were molecules that would give off or release H+1 ions. They were molecules that would increase the concentration of H+1 ions in the solution. So what kind of formula would an acid have? So since it's giving off H+1 ions, every acid has an H+1 ion in the formula. And a positive ion is always going to be attached to some negative ion. So there's some random negative ion, let's call it X at the moment. So every acid has this formula, that is that it has an H+1 ion attached to some negative ion. So for example, our first acid, that's H+1, and you can attach it to Cl-1. Cl is group 7. So the formula, so our formula is HCl, which is hydrochloric acid. So it's made up of H+1 attached to a negative ion. We can have another acid, which is, let's say, H+1, and we can attach it to sulfate ion, which is SO4, and it has a charge of -2. Now the formula of this acid, if you do crisscross, if you remember crisscross, that's there's going to be 2H and there's going to be 1 SO4. So it's going to be H2. So there would be 2 hydrogen ions, and there's going to be 1 SO4, and that's going to be called your sulfuric acid. So keep this idea in your head that every acid has an H+1 ion, because that's what it's going to release when you dissolve it in water. Every acid has an H+1 ion, which is attached to some random negative ion. So here's a complete list of acids that I've written for you. You can pick any H+1 ion, attach it to any negative ion, that's going to be your acid. So HCl, H2SO4, that's sulfuric acid. We've already done that. H+1 with nitrate ions, that's going to be nitric acid. H+1 with carbonate ion, if you do crisscross, there's going to be 2 H's and 1 CO3, so H2CO3, that's carbonic acid. H+1 attached to SO3 -2, you do crisscross, that's going to be sulfurous acid. H+1 with nitrite ions, NO2 -1, That's going to be nitrous acid. H plus 1 with phosphite ion. That's going to be phosphoric acid. And we've got H plus 1 with PO3 minus 3, which is phosphite, and that's going to be phosphorus acid. So remember the names and the formulas of all of these acids. That's extremely important. And let me also quickly define the terms strong acid. Strong acid is, now most of these acids are strong acids. They're known as mineral acids, except for this carbonic acid. The ones with carbon, they're normally weak acids. We're going to come to weak acids later on as well. So strong acids, they ionize fully or completely in aqueous state and produce more H plus 1 ions. What that means is that I've got water over here. Water has some of the water molecules have dissociated as well. They've produced H plus 1 and OH ions. Right now it's neutral, so the quantity of H plus 1 and OH ions that's equal. Now what if I start adding HCl into this? So if I add HCl, and let's say I add 2 molecules of HCl. So there's another molecule of HCl, and let's say I add 2 molecules of HCl. What's going to happen is that HCl is a strong acid, so all of the HCl molecules will dissociate. They're going to break down and they're going to produce H plus 1 and Cl minus 1 ions. Remember, hydrochloric acid was made up of these 2 ions, so when I mix them in water, they break down, they ionize, and they produce H plus 1 and Cl ions. The other HCl molecule will also ionize and it will produce H plus 1 and Cl minus 1 ions. So that is what is meant by fully ionizing. That means that every single HCl molecule that I add, if I add a third HCl molecule into water, that HCl molecule will also ionize and it would produce H plus 1 and Cl minus 1 ions in solution. And what that does is that you can see over here, or you can note over here, is that the quantity of H plus 1 ions is a lot higher in solution because the acid is constantly producing them. There were already some H plus 1 ions present, but now that quantity is a lot higher compared to the quantity of OH ions. There's only one OH ion over here at the moment. Now we're going to talk about what a weak acid is. So the definition of a weak acid that you're going to write in your exam is that a weak acid ionizes partially or weakly in aqueous state and produces a lot fewer H plus 1 ions. An example of a weak acid in the example of acids that I've written over here, one of them is carbonic acid. That's definitely a weak acid. Most organic acids are weak acids. Now, here's an example of weak acids, organic acids, which we are not doing at the moment. That will be done separately in organic chemistry. Organic acids are considered to be weak acids. Organic acids have this structure, they ionize, but they ionize very little. So they always have this reversible sign when you write an equation for a weak acid ionizing, because it's not going to completely ionize. So what that means is that if I have so they're not going to ionize fully. So if I add molecules of carboxylic acid, organic acids in water. So here's my water, and I'm adding carboxylic acid into water. What's going to happen is, and let's say I add 2 of them. Then what's going to happen is that maybe one of them ionizes and it produces the ion RCO minus 1 and releases an H plus 1. While the other molecule might not ionize, it will remain as carboxylic acid and the H plus 1 is not going to get produced. So the organic acids, they tend to be very weak. They're actually much weaker. You add 1,000 molecules and maybe one of them just ionizes. The others refuse or they don't let go of their H plus 1 ions. So organic acids are mostly weak acids, which we are, again, I'm repeating, not doing in this lecture at the moment. We'll do those separately in organic chemistry. But make sure you know what organic acids are. And I'll write an equation for a strong acid ionizing as well. So for example, if I have sulfuric acid, which is H2SO4, I add it in water, there's not going to be a reversible sign because the sulfuric acid is a strong acid and it will produce or break down into H plus 1 and SO4 minus 2 ions. And there's going to be 2 H plus 1 ions that are going to be produced when a strong acid like sulfuric acid ionizes, because remember the formula crisscross we did, there's going to be 2 H ions and 1 sulfate ions. These were the ions that made up sulfuric acid over here. So when it breaks down and when they're separate, when the acid has ionized and the ions are separate, you don't write small 2. Small 2 is always written when they are together, when they are forming one compound. But once they have dissociated, once they have broken down and they have separated, you don't write the small 2. So 2 hydrogen ions over here, now you've got 2 separate hydrogen ions. So you write a big 2 in front of it. that shows that there are two hydrogen ions that are produced, but they are separate from each other now. And there's one sulfate ion that's produced over here. If I write the same equation for phosphoric acid, ionizing, then that's going to look like this, that it's going to produce 3H+1 ions, and it's going to produce one phosphate ion when it's dissolved in water. So this is phosphoric acid over here. It was made up of H+1 and PO4 minus 3 ions. We did crisscross, and that showed that there should be 3 H ions and 1 phosphate ion. So, but once it has dissociated, so 3 capital big 3 in front of it, 3 H+1 ions that are separate. Now they're roaming around separately in water. So make sure how to write the equation for acid dissociation. So these are your list of acids. Just make sure you remember this list by heart. So we're gonna now quickly move towards bases and their formulas. Let's now start talking about bases and their formulas. The first thing is, so bases are proton acceptors. They were molecules that would accept H+1 ions. So they could be anything. They could be ions, molecules, etc., which are capable of accepting and attracting H+1 ions. So the bases that we are going to deal with, the common bases are, so our common bases are oxides, hydroxides, carbonates, and ammonia. An oxide ion is O-2. A hydroxide is OH-1. Carbonates are also weakly basic, so they are CO3-2. And ammonia. Ammonia is a gas. It's a pungent smelling, very sharp smelling gas. So that's ammonia. That's also a strong base. Now they're all capable of accepting H+1 ions. For example, oxides, if they see H+1 ions, they're going to attract H+1 ions, and with H+1 ions, they all would form H2O. Is going to be water is going to be produced. So 2 H+1 ions, so O-2 is going to attract 2 H+1 ions. OH-1, these ions, they also do something similar. They're going to attract H+1 ions, and they're also going to form water molecules as well. Carbonate would do something similar. It's also going to attract H plus ions, 2 of them. And what actually happens with carbonates is that one of the oxygens, it attracts the H+1 ions, and they end up forming water. And what's left is carbon dioxide. So with carbonates, always carbon dioxide is also produced. So oxygen in the carbonate would attract the H+1, form water, and one oxygen leaves, and what's left is carbon dioxide. And the last thing is ammonia also does exactly the same. It attracts H positive ions. So it's also going to attract H+1. And it ends up forming this ion, which is ammonium ion. H+1 attaches to it, so it becomes NH4+1, which is that's your ammonium ion. This was your sharp, pungent smelling ammonia gas. So that also does something similar. So all of them, oxides and our hydroxides and our carbonates and ammonia gas, they're all basic because they're all capable of accepting H+1 ions. So if you add them in water, the amount of H+1 ions is going to decrease because they're going to gain those H+1 ions. Then you often also get the question, what are alkalis? Alkalis are your soluble bases. So whenever you see an alkali, it's still a base. It could be any of them as long as they are soluble. They dissolve in water, and that they would always make an alkaline solution. So which of these compounds are soluble? So the soluble oxides and hydroxides, all group 1 hydroxides and oxides are soluble. For example, you've got NOH or KOH. They are going to be soluble, and they're going to be very strong alkalis because they're going to dissolve and mix in water a lot easily. And then there are some in group 2 as well that are soluble. Especially those that are lower down in group 2, like barium hydroxide, strontium hydroxide, and partially calcium hydroxide. So the elements that are below in the lower part of group 2, their hydroxides and oxides are also soluble. And one more, which is ammonium hydroxide. That is also, ammonium compounds are all soluble as well, or you can also call this aqueous ammonia. Both of these bases are going to be soluble as well. Now we're going to quickly jump towards reactions, and a lot of chemistry reactions are of reactions of acids and bases with each other. So any reaction that's related to acids and bases, we're going to talk about it. So the first reaction that we are starting with is metal plus acid. It produces salt plus H2 gas. Salt are the neutral compounds that are produced when an acid reacts with a base, or when an acid gets neutralized. So let's start with our first reaction, which is let's do sodium reaction with HCl. what's going to be produced is a salt and an H2 gas molecule. So what will happen is the Na is going to come and it's going to displace the H over here, and as a result, the H is going to get knocked out. Na is going to take its place. So Na is going to come in and knock out the H. So Na is going to take its place. Make sure you do crisscross again. Na is in group 1, so it's +1. Cl is in group 7, so it's -1. So that is the formula. NaCl is going to be NaCl, just NaCl, even if you do crisscross. And the H that gets displaced would form H2 gas molecule. So that looks like my final equation. Now, whenever you make an equation, that's it. So metal comes in, knocks out the H, and salt plus H2 gas is produced. We can do another reaction. For example, we can have magnesium reacting with phosphoric acid. Remember, we wrote down a list of acids, so make sure you remember what acid is. What are the ions that make up the acid as well? Phosphoric acid was made up of H plus 1 and PO4 minus 3 ions. Again, what's going to happen is that the Mg is going to come in and it's going to knock out the hydrogen and it's going to take its place. So you're going to get Mg, the H are gone, Mg and PO4. Make sure you do crisscross again. PO4 had a charge of -3. Mg was in group 2, so it had a charge of +2. So the formula would be, if you do crisscross, there's going to be 3 Mgs and there's going to be 2 phosphates. And the hydrogen is going to get displaced, so it's going to form H2 gas molecule. That's your second equation. Now, every equation that you make, it has to be balanced. Once you make the formulas, make sure you don't change the formula. You don't have to worry about that there are 3 H's here, but there's an H2 gas over here. Forget everything. Remember, I told you that H2 gas is going to be produced, so you just write down H2. So the first thing is you just write down the formulas. Make sure you write down the formulas correctly, and then you balance afterwards. So for example, this equation is clearly unbalanced. The H atoms over here, there are 2 H atoms. So there should be 2 H atoms over here as well. So I'm going to double the amount of HCl molecules. I'm going to have 2 HCl. Remember, just think of these as imaginary brackets. So I'm going to have 2 HCl molecules. So now the hydrogens are balanced. But if I have 2 HCl molecules, there's going to be 2 Cls on the left side. So there should be 2 Cls over here as well. Now I can't change the formula. What I can do is I can double the amount of NaCl that's being produced. So now I do have 2 Cls. But if I have 2 NaCls, there should be 2 sodiums on this side. So there should be 2 sodiums over here as well. So I'm going to double that as well. So now this equation is balanced, where the atoms on both sides are now equal. We can try with the other one as well. We can look at Mg first. There are 3 magnesiums over here, so I can have 3 magnesiums on this side as well. So Mg is balanced. Now, if I look at hydrogens, you would notice, or PO4s, there are 2 PO4s over here in the formula. So there's only 1 PO4. So what I can do is I can double my phosphate ions. There were 2 phosphate ions. Now I've got 1 phosphate ions, but there are 2 molecules now, so that's 2 phosphate ions as well. But if I double this, that's if I have 2 molecules, I'm going to have 6 hydrogens over here. So what number should I multiply this with? This should be multiplied by, I need 6. So there should be 3 H2 gas molecules. Now every element is balanced now. Now let's practice a few more equations. I've written down different metals reacting with acids. This is nitric acid. So every time it's going to be salt plus H2 gas. So I've written down H2 gas as well. Now what's going to happen is that aluminium is going to come in and it's going to knock out this hydrogen over here. So it's going to be aluminium and the H is knocked out. So Al and NO3. And I'm going to do crisscross. Aluminium is in group 3, so it's +3. NO3 is, nitrate is -1. So the formula of this compound is going to be Al NO3 thrice. So that's aluminium nitrate. The next one is barium with sulfuric acid. So barium is going to come in and it's going to knock out the hydrogen over here. So it's going to be barium and SO4. Now barium is group 2, so it's +2. SO4 is sulfate is -2, so it's just going to be barium sulfate. That's it. You don't need to do crisscross because the charges are already equal. The next one is K is going to come in and knock out the H in the phosphorus acid. So it's going to become K and PO3. Now K is group 1, so it's +1. PO3 has a charge of -3, so it's going to be K3PO3. And then finally the last one, which is calcium with HCl. Calcium is going to come in, knock out the H. So it's going to become calcium and Cl. Calcium is group 2, so it's +2. Cl is group 7, so it's -1. So it's going to be crisscross. It's going to be CaCl2. So those are my formulas. And after I make the formulas, the charges are already there, but I'm not going to write those charges once the formulas are made. So I'm just going to clean up the equation. So those are my formulas. And the final thing is we need to balance each one of these equations. So these are my products every time H2 gas is going to be produced every time. So I need to balance every equation over here. So let's look at this one. There are 3 nitrate ions. So what I'm going to do is I'm going to multiply my nitric acid with 3. So now I have 3 molecules. So I'm going to have 3 nitrate ions as well. So that is balanced. The H's, if you look at the H's, there are 3 H's and there are 2 H's over here. Now I can't multiply any number here which is going to give me 3 H's. So what I can do is I can double everything up. What I can do is I can have 6 H's, and over here I can have 3 H2 gas molecules then. So that way my H's would be balanced because there are 6 H's because I've got 6 nitric acid molecules and I've got 3 molecules of H2. So that's also 6 H's. But that would make it 6 nitrate ions as well. So this one over here has only 3 nitrate ions. So I need to double this as well. So now one molecule had 3 nitrate ions, but now we've got 2 molecules, so they're going to have 6 nitrate ions. Aluminium would also get doubled, so I need to have 2 aluminiums on this side. So now this equation looks perfectly balanced. Let's move to the next one. The next one is already balanced. There's 1 barium, 1 barium, there's 1 sulfate, 1 sulfate, there's 2 H's, 2 H's, so it's already balanced. The third one, again, you got 3 H's and you got 2 H's. So what I'm going to do is I'm going to multiply this by 2. So that way, I'm going to have, if I have 2 phosphorus acid molecules, I'm going to have 6 H's. And I'm going to multiply this by 3. So that will also give me 6 H's in my products as well. And now PO3, there's only one, but now we got 2 molecules, so that's 2 phosphide ions. So I need to double on my right side as well. So that's also 2 phosphide. The case, there were 3 of them, but there are 2 molecules now, so that's 6 potassiums. So got to double this. So you got 6 potassiums. This one, Cls are 2. There's only 1 Cl, so let's double this. And now it's balanced. The H's are doubled as well. There are 2 H's, so now all of these equations are balanced. So remember that metal plus acid produces salt plus H2 gas molecules, and you should be aware of these equations. And here's an image of magnesium reacting with sulfuric acid. You can see magnesium metal, a strip of magnesium metal. As soon as you put it in acid, you're going to start noticing bubbles of H2 gas being produced. So the main observation over here during all of these reactions is that so effervescence of H2 gas is produced and the metal would be seen to be dissolving. And there's another thing about this is that not all metals are going to react vigorously, or some would have very slow reactions, some would have very, very fast reactions. Metals have different reactivities. So you should also be aware of the reactivity of metals. That's a separate topic, but the reactivity of metals, group 1 metals, and those lower down in group 2, they're highly reactive metals. So they're going to have very, very explosive reactions. So for example, so if you want to see sodium reacting with an So here's sodium metal reacting with an acid. It's going to be explosive reaction. So never try doing this in the lab because it's going to be highly, highly explosive. Now the metals that are slightly lower down in the reactivity series are magnesium, aluminium, zinc, iron, and tin, which I would refer to as mazet metals. Magnesium, aluminium, zinc, iron, and tin. These metals are not too reactive, so they have normal moderate reactions. They don't have vigorous. They can be safely. You can safely do these reactions in the lab. So for the above reactions, all of these, it's recommended that you use these particular metals because it's going to be safe to perform these reactions in the lab. Now, as you go lower down in the reactivity series, the very unreactive metals like silver, gold, etc., they won't react with dilute acids. If they were to react, they would probably react with very, very concentrated acids at very high temperatures. These metals are highly unreactive, so you don't really expect a reaction when you add a metal like copper or silver to an acid. We're now going to try and do a second reaction, which is a metal oxide or hydroxide reacting with an acid to produce salt plus H2O. Now remember that we did that oxides and hydroxides were basic because they're going to accept H plus 1 from the acid and they're going to produce water. So oxides and hydroxides. And also remember one thing, that oxides and hydroxides are kind of the same thing. What happens is that when you have an oxide, for example, if I have magnesium oxide that's Mg plus 2, O minus 2. If I add H2O to it, so if water gets added to it, it's going to turn into a hydroxide. So it's going to become Mg, and OH is minus 1, so Mg plus 2, OH minus 1, so it's going to be MgOH2. So also always remember that an oxide, you add water to it, it becomes a hydroxide. You heat it, you remove water from it, it will turn back into an oxide. So oxides and hydroxides, they kind of tend to be the same thing, except that you remove water, you get an oxide. You add water, you get a hydroxide. Now coming back to our reaction, the first reaction I'm going to do is sodium hydroxide, which is sodium is group 1, so it's plus 1. Hydroxide is OH and it's got a charge of minus 1, so that's sodium hydroxide. I'm going to react it with an acid. Let's say take hydrochloric acid, that's HCl, H plus 1 and Cl minus 1. Now the reaction is going to be that the H plus 1 from the acid and the OH minus 1 that's coming from the base, they're going to react together and they would end up producing a H2O molecule. So they're going to produce water. Water is always going to be produced. The H and the OH are going to combine and they're going to form water. And what's left is your salt. That's Na plus 1 and Cl is group 7. So that's minus 1. So it's going to be Na plus 1 and Cl minus 1. And that's going to be my salt. So all of these reactions are going to be very, very similar. Let's do another one. Let's take magnesium hydroxide. Mg is group 2, so it's plus 2. Hydroxide is OH and it's got a charge of minus 1. So the formula is going to be Mg, OH twice. Plus, let's take nitric acid. Nitric acid is HNO3. So it's H plus 1 and NO3 minus 1. And again, the same thing is going to happen. The H plus 1 from the acid and the OH minus 1 from the base, they're going to combine and they would end up forming H2O. So you get an H2O molecule. And what's left is your salt. So what is left? It's magnesium ions and nitrate ions. Mg plus 2 is left. And NO3 minus 1 is left. And you're going to do crisscross again. So it's going to be Mg1. And NO3 is going to be twice. So that's magnesium nitrate. That's going to be my salt. Let's do another one, aluminium hydroxide. So aluminium is group 3. It's plus 3. OH is minus 1. So the formula is going to be Al. OH thrice. Plus, let's react it with sulfuric acid. That's H2SO4. So that's H plus 1 and SO4 minus 2 combined together. And again, the same thing would happen. The OH minus 1 and your H plus 1 in the acid, they're going to combine together and they will end up forming H2O molecules. And what's left is your salt. So what is left? Al is left and SO4 minus 2 is left. So you got Al, which is Al group 3, that's plus 3, and you got SO4, which is minus 2. So it's going to be Al2 and SO4 would be thrice. Let's do equations with oxides as well. So sodium oxide, so sodium is group 1, so it's plus 1. Oxide is oxygen, it's group 6, so it's minus 2. So the formula is going to be Na2O. And I'm going to react it with phosphoric acid, that's H3, PO4. And again, what's going to happen is that the oxide now reacts with the H plus 1 that's coming from the acid. They're going to react together and water is going to be formed. So a water molecule gets produced. And what's left is your salt. So what's left is you've got Na, which is plus 1, and PO4, which is minus 3. So Na, that's plus 1. And I've got PO4, which is minus 3. So if I do crisscross, it's going to be Na3, PO4. Just make sure when you're making this salt formula, forget that how many sodium ions you got on that side or how many phosphate ions. Just make sure that you got Na plus 1 and PO4 minus 3. Do the crisscross again. You're going to do the balancing stuff right at the end. So make sure, ignore the fact that there's 2 sodium ions. You just need to know what ions are present over here and you combine them to form the salt over here. And we're going to balance them at the end. So let's do another one, which is let's do magnesium oxide. Mg is plus 2 and group 2, so oxygen is minus 2. So the formula is just going to be MgO in this case. And let's react it with phosphorus acid, which is H3, PO3. And again, your product is going to be, you've got H and you've got O. So now water gets produced, H and O combine, and what's left is your salt. So it's Mg and PO3. So my salt, the formula of my salt is going to be, I've got Mg, which is group 2, so it's plus 2, and PO3, is phosphide. It's got a -3 charge. So if I do crisscross, it's going to be 3 mgs and there's going to be 2 phosphate, and that's going to be the formula of my salt. Let's do another one for transition metals. For example, if I have copper 2 hydroxide, for transition metal, the charges would be written in the formula. So copper 2 hydroxide means that copper is +2, hydroxide is OH, and it's got a charge of -1. So the formula, crisscross, it's going to be COH2. And I'm going to react it with nitric acid. So that's HNO3, H+1, and NO3 -1. And again, the OH and your H from the acid are going to combine together to form H2O molecule. And what's left is your salt, so it's copper and NO3 that's left. So NO3 was -1, copper was actually +2, so it's going to be CuNO3 would be twice. So now I've made plenty of equations. What I'm going to do is I'm going to rub off the charges because the charges are there, but you don't write the charges on the formulas. So here are all my equations after I've cleaned them up, removed all the charges that were written on top for the working. Now I'm going to try and balance them. So remember, one trick about balancing complicated equations is you have to make the number of elements equal on both sides. But one rule that you should follow is, so start with balancing the easiest first. These are elements that appear in the least number of places. So for example, if I look at the first equation, although it's already balanced, but so we're gonna ignore the first equation. Everything is balanced. There are two hydrogens. Everything is balanced in the first equation. We're going to focus on the second equation. Now, in the second equation, I'm going to start off with balancing magnesium. Why magnesium? Because that's the easiest. You got magnesium over here and you've got magnesium over here. That's it. So it's in two places and it's already balanced. There's one magnesium and there's one magnesium. So start with the easiest. I'm going to put tick marks in front. So magnesium is done already. That was the easiest. Which one is next? We're gonna focus on nitrate, or we can focus on nitrogen. You can either balance nitrate together, or you can just focus on the element nitrogen. So there are two nitrogens over here. NO3 has one N, but in brackets it's twice, so that's two N's. There's only one N over here, so I'm going to balance it. So I'm going to just multiply it with 2. That's it. So I'll have two nitric acid molecules. That's going to give me two nitrogens. So nitrogen is also balanced. Now the next one I'm going to balance is, I've got hydrogen and oxygen left. Oxygen is in 1, 2, 3, 4 places. I'm not going to balance it first because it's going to be too difficult. I'm going to focus on the easy ones. H is over here, and over here. H is in 3 places. So we're going to focus on H now. So how many H's on the left side? OH twice, that's 2 hydrogens. 2 nitric acid, that's also 2 hydrogens. So in total I've got 4 hydrogens over here. So what do I need to multiply this with? I'm going to multiply this with 2, so I can have 4 hydrogens, and that's going to balance the H atoms. Now the last one, which is oxygen, is automatically balanced. There are 2 oxygens, and there are 6 oxygens over here. 2 nitric acid, that would give me 6 oxygens. OH twice, that's going to give me 2 oxygens. So that's a total of 8 oxygens. Nitrate twice, that's 6 oxygens, and 2 water molecules, that's also 2 oxygens. So that's 8 oxygens. So the last one automatically gets balanced. And we can apply the same technique on the next one as well. So if you focus on the next one, I'm going to start with the easiest, which looks to be aluminium. Least number of places. Let's try and balance aluminium first. So I've got 2 aluminiums over here. So I've got 2 aluminiums on that side. So I need to have 2 aluminiums over here as well. So I'm going to multiply this entire thing with 2, because there was only 1 aluminium. Now there's going to be 2 aluminiums over here. So aluminium is balanced. Let's focus on the next one, which is the easier one. That's I'm going to go with sulfur, because that's appearing in 2 places only. So let's focus on sulfur. Sulfur over here, SO4 only has 1 sulfur, and it's thrice, so that means you got 3 sulfurs over here. This molecule over here has 1 sulfur over here, so I need to multiply this with 3 as well. So I'll have 3 sulfuric acid molecules. That's going to give me 3 sulfurs. So sulfur is balanced as well, and I'm just going to repeat this. SO4 had 1 sulfur, brackets thrice, that means there are 3 SO4s, that means I've got 3 sulfurs. There was 1 sulfur over here in the molecule, and multiplied it by 3. So you got 3 sulfuric acid molecules. Let's focus on the next one. Oxygen, 1, 2, 3, 4. So don't balance oxygen. That's going to be too hard. Focus on hydrogen. That's over here, and over here. So I'm going to go with hydrogen. That is slightly easier to balance. So how many hydrogens do I have? OH thrice, that's 3 hydrogens. But I've got 2 molecules. So that means I've got 6 hydrogens over here. And sulfuric acid has 2, but I've got 3 molecules. So that means I've got 6. So 6 hydrogens here, so that's a total of 12. So I need 12 hydrogens on the right side as well. So I'm going to multiply this by 6. I'm going to get 12 hydrogens. Now the last one is oxygen, which should be balanced automatically. You can count the oxygens. 6 oxygens over here. OH thrice, that's 3. 2 molecules, that would give you 6 oxygens. And let me put this to the side a little bit. And then, so I've got 6 oxygens. I've got 12 oxygens over here. That's a total of 18. 3 sulfuric acid, that's 12 oxygens. SO4 thrice, that's 12 oxygens. And there are 6 oxygens over here. That's also 18. So oxygen is automatically balanced. Let's try and do the next one. Remember, easy first. Sodium, 2 places. So how do I balance them? There are 2 sodiums on this side, and there are 3 sodiums on the other side. What do I multiply each with? So I can multiply this with 3. So that's going to give me 6 sodiums, and I'm going to multiply this by 2. That's also going to give me 6 sodiums. So the first one, the easy one, that's out of the way. I've got 6 sodiums on both sides. We can focus on the next easy one, which is, let's focus on P. In the entire molecule, there's only 1 P, but there are 2 molecules, so that's 2 P's. There's 1 P in this molecule, so I'm going to multiply this by 2 as well. So 2 phosphoric acid molecules. So P is also balanced. That was the easy one, just appearing in 2 places. Let's focus on H now. It's also appearing in just 2 places. So 6 H's, 2 molecules, so that's 6 H's. I need to multiply this with 3. That's going to give me 6 H's on the right side as well. And finally, oxygen over here. So H is done. And finally, oxygen, 3 oxygens, 8 oxygens, so that's 11. 8 oxygens because there's 4 and there are 2 molecules, so that's 8 plus 3, that's 11. So oxygen is also balanced automatically. Let's jump to the next one. Easy ones, 3 Mg. So this should be multiplied by 3. So Mg is done, the first one. Next one, easy ones. Let's focus on P. PO3 has 1 P, but twice. That means you got 2 P's. There's only 1 P on this side, so I'm going to multiply this entire thing by 2. So I'm done with phosphorus. Focus on easy ones. O is the difficult one. It's everywhere. H is slightly easier. There are 6 H's. So over here, I need to multiply this with 3. And that's going to give me 6 H's. So H is done as well. And oxygen should automatically get balanced. 3 oxygens, 6 oxygens, that's 9 total on the left side. PO3 twice, that's 6 oxygens, and 3 oxygens, that's also 9. So oxygen is also automatically balanced. And let's quickly do the last one, which is copper is already done, easy ones. NO3 has 1 N, and that's twice, so that's 2 N's. So I need to multiply this by 2. And we can focus on H, 2 H's. 2 H's here as well, that's 4 H's. So multiply on the right side, I'm going to multiply it with 2, so I have 4 H's. And oxygen should be balanced. 2 oxygens, 6 oxygens, that's 8. 6 oxygens and 2 oxygens, that's 8 as well. So remember how to balance equations, practice a lot. You can go through this video again, very slowly. Try and do these equations yourself. And you can make any metal oxide, metal hydroxide equation reacted with an acid. It's going to produce salt and H2O. Now let's try and do the third reaction of carbonates reacting with acids, and they're going to produce salt, water, and carbon dioxide. Now we had already previously discussed that carbonates were basic. Carbonates had an oxygen in them, which would grab an H+1, form water with it. And once that oxygen is left, you would be left with carbon dioxide. So you would always see bubbles of carbon dioxide gas produced when you react a carbonate with an acid. So let's say I've got sodium carbonate. Sodium carbonate is sodium Na group 1 plus 1. Carbonate is your CO3 minus 2 ion. And if I do crisscross, it's going to be Na2 CO3. I react it with an acid. Let's take the simplest one, hydrochloric acid, HCl. Now, when these two react, the H from the acid and the carbonate, which we just discussed, are going to react together, and they're going to end up producing water and carbon dioxide. So water and CO2 gas is produced. The carbonate, the oxygen reacts with the H, forms water, and what's left is carbon dioxide. And what are the ions left? That's going to be your salt. So Na ions and Cl ions are left, and so your salt in this case would be Na plus 1 and Cl minus 1 are left. So they're going to form your salt, which is going to be NaCl in this case. So that's going to be my reaction of sodium carbonate reacting with an HCl molecule to produce salt, water, and carbon dioxide. So let's try another one. Let's do magnesium carbonate. Magnesium is group 2, it's plus 2, and carbonate is CO3, and it's minus 2. Let's react it with phosphoric acid, that's H3, PO4. So remember the name of your acids. Now again, when these are going to react, the H from the acid and the carbonate would react, and they would form salt, water, and carbon dioxide. So water gets produced along with carbon dioxide gas molecules, and what's left is going to be a salt. So Mg ions and PO4 ions are going to combine to form a salt, which is going to be Mg and PO4. But Mg is group 2, so it has a charge of plus 2. PO4 is minus 3. So the formula of the salt would be Mg thrice, and PO4 would be twice. Now next one, let's do aluminum carbonate, which is Al is plus 3. Carbonate is minus 2. So formula क्या होगा? That's going to be Al2, and CO3 would be thrice. And let's react it with कौन सा acid? Let's pick HCl, hydrochloric acid, H plus 1, Cl minus 1. And when this happens, so the reaction is going to be that, again, same thing, H and the carbonate would combine to form what? They're going to form water and carbon dioxide. So water plus carbon dioxide. And what's left is your salt, Al and Cl. So make sure you remember the formula: Al lines, Cl lines. Al is group 3, it's plus 3, Cl is minus 1, so it's going to be Al, Cl3. All our formulas are made now, and that's it. That's your salt, water, and carbon dioxide. So let's quickly do another one. Barium. Let's do barium carbonate. Barium is group 2, it's plus 2. Carbonate is CO3 and it's minus 2. So the charges are equal, don't do anything. Don't do crisscross. React it with nitric acid. So that's HNO3, H plus 1, NO3 minus 1. And again, the same thing. The H and the carbonate would react, and they would form what? They would form water and carbon dioxide. And what's left is your salt. So Ba and NO3, that's what's left. So these two ions would combine to form the salt, Ba and NO3. NO3 is minus 1, Ba is plus 2. The formula क्या होगा? It's going to be Ba, and NO3 is going to be twice. So we're going to add twice over here. So that's going to be my salt, water, and carbon dioxide. The next one, let's do iron 3 carbonate. Transition metals, the charges are in the name itself. So iron 3 carbonate would be, iron would be plus 3. And what's carbonate? Carbonate is CO3, it's minus 2. So the formula is going to be Fe2, and CO3 would be thrice. Let's react it with the sulfuric acid. So that's H2SO4. And again, the H and the carbonate in the other compound, they would react, and they would form water, and they would form carbon dioxide. And what's left is your salt. So iron and sulfate ions are left. So iron is plus 3, and sulfate is SO4, and it's minus 2. So the formula is going to be Fe2SO4 thrice. And that's going to be the formula of my salt. What I'm going to do now is I'm going to clean up the charges. Charges are normally not written. So get rid of the charges. The charges are there, but you don't write them in the formula. So I'm getting rid of all the working Na plus 1 Cl. You just call it NaCl. Magnesium phosphate, aluminium chloride, barium nitrate, and this one. Now let's try and balance all of these equations, starting with the first one. And remember, balance the easiest first. So in the first equation, Na, easy ones, the ones that appear only in two places. Na, there are two Nas. So there's only one Na over here. I'm going to just double this. So now the Na is balanced. Easy one. Cl, there's one, but there are two molecules now, so that's two Cls. So there's only one Cl over here. I'm going to double that as well. H's, there are two of them over here, and there are two H's over here, so that's balanced. Carbon, there's one that's balanced. So if everything is balanced, the last one would automatically get balanced as well. So the oxygen, which is 3. So how many oxygens? I've got 2 and 1, that's 3 as well, so that's balanced. Let's move to the next one. Start balancing the easy ones. There are 3 mgs. So what I'm going to do is I'm going to, there's only 1 mg over here. So what I'm going to do is I'm going to multiply this with 3. And remember, these brackets are just imaginary brackets. Think of them as imaginary brackets. The brackets are usually not written over there. So 3 magnesium carbonates, easy ones. Phosphorus, there's 1 over here, but they're twice. So that's 2 phosphoruses. There's 1 P over here. There should be 2, so I'm going to double this. So P is balanced. Again, easy ones. Carbon, there's 1 over here in the formula. There are 3 molecules, so that's 3 carbons. There's 1 carbon, so I'm going to multiply this by 3. So now I've got 3 carbons. Again, the easy one is H. There are 6 of them over here, so I'm going to multiply the H over here. I'm going to make it 6 as well. Now, since I've balanced everything, the difficult one, oxygen, was in 5 places. So oxygen should be balanced automatically. There are 9 oxygens over here. There are 8 oxygens over here, so that's 8 plus 9, 17. There are 8 oxygens over here, and 3 over here, and there are 6 oxygens over here, so that's also adding up to 17. So the last one, the difficult one, should balance automatically. Now the next equation, again starting with the easy ones, we're going to pick aluminium 2. So there should be 2 aluminiums on the right side, so I'm going to multiply this by 2. Easy ones. Cl in 2 places. So Cl, there are 3, but there are 2 molecules, so that's 6 Cls. So I'm going to multiply this with 6, so I can have 6 Cls over here. So Cl is also balanced. Carbon, how many carbons in the iron? There's only 1 carbon, but it's thrice, so that means you got 3 carbons. So I'm going to multiply this with 3 because the formula only had 1 carbon, so now it's got 3 carbons. Hydrogens, there are 6 over here, so I need to multiply this with 3. So I can have 6 H's over here as well. So that also is automatically balanced. And oxygen would automatically get balanced. How many oxygens? I've got 9 oxygens over here. CO3 thrice, so that's 9 oxygens. How many oxygens? I've got 6 oxygens over here. And I've got 3 oxygens over here. So that's also a total of 9 oxygens. So oxygen over here has automatically gotten balanced as well. Let's move on to the second last one and quickly do that. Barium, easy ones, that's already balanced. Carbon looks to be balanced. There's 1 carbon, there's 1 carbon, so that's also balanced. So N over here, there's 1 in the formula and it's twice, so that's 2 N's. There's only 1 N over here, so I need to make it 2. So I'm going to double this. So N is balanced, and now the whole equation looks balanced. The H is also balanced. There are 2 H's, so that's also balanced. So the last one, the oxygen, should be balanced automatically. The difficult one, oxygen is everywhere. So 3 oxygens, 6 oxygens. So that's 6 plus 3, that's 9. 6 oxygens because it's NO3 twice, so that's 6 oxygens. There's 1, so that's 7, and there are 2, that's 9. So oxygen is balanced. Let's do the last one. Fe, easy ones, that's balanced already. 2 Fe's, 2 Fe's, both sides. Carbon, that's 3 of them over here. CO3 has 1 carbon, but it's thrice, so that's 3 carbon. So I'm going to balance the carbon. So that's balanced. And sulfur, there are 3 of them. SO4 has 1 sulfur, but it's thrice, so that's 3 sulfur. So I'm going to multiply this with 3 because this formula had only 1 sulfur. So I've multiplied it by 3. So I got 3 molecules. H's, there are 6 of them, so I'm going to multiply the water with, so I've got 6 H's. And finally, the oxygen should be balanced. It should automatically get balanced. 9 oxygens, 12 oxygens, so the 12 plus 9 is what, 21? SO4 thrice, that's 12, plus 3, that's 15. 15 plus 6 oxygens, that's 21 as well. So the last one automatically gets balanced as well. Now the last reaction that we're going to do is ammonia plus acid, and that's going to produce ammonium salt. So remember, ammonia was basic as well because ammonia would attract or grab an H plus 1, it would accept an H plus 1, and it will form ammonium ions. And that's what's exactly going to happen with ammonia equations as well. So these equations are kind of really, really easy to make. So I've got ammonia, and I'm going to react it with HCl. So what's going to happen is that my ammonia over here is going to attract that H plus one, and it will form ammonium ions. It's going to form NH4 plus one. And what's left is Cl minus one. So Cl is left. So it's going to be ammonium and Cl ions. So this is ammonium chloride. That's the salt produced. And we can keep on making equations with other acids as well. Ammonia plus sulfuric acid. So that's H2SO4. Same thing would happen. The ammonia over here will attract the H plus one from the acid, and they're going to produce ammonium ions again. And what's left is SO4 minus 2. That's what's left. And if you do crisscross, it's going to be NH4 would be twice. According to the formula, it's going to be, if you do crisscross, it's going to be 2 NH4s and 1 SO4. And you can balance this. So there are 2 ends. So you can write 2 over here, and that should balance things out. Now this one is ammonium sulfate. So let's make 2 more of these equations. Ammonia over here will attract the H plus one. So ammonia from phosphoric acid will attract the H plus one. And again, it's going to form ammonium ions, NH4 plus 1, and what's left is PO4 minus 3. So NH4 would be thrice. So that's ammonium phosphate. Next one, that's ammonia again, attracting the H from the acid, and they're going to produce ammonium ions, and NO3 minus 1 is left. So that's going to be ammonium nitrate. And you can balance each one of the equations. The only thing is that 3 NH4, so there should be 3 NH3s, and that should hopefully balance it. There's 1 NH4, so that's kind of already balanced. So just remember that that ammonia reacting with an acid would produce an ammonium salt. Now we are going to quickly discuss solubility of salts. You've got all sorts of salts that we have discussed earlier. We've made a number of equations. Our board is full of equations. So all of them had salts being produced, all sorts of compounds basically. Now we're going to discuss which ones are soluble, which are going to mix in water, and which ones are not going to mix in water. Now, one thing about dissolving that you should remember is that when you dissolve a substance, for example, this is NaCl. So there's what we can say is that there is now NaCl is an ionic lattice. There's solid NaCl, and I'm trying to mix it in water. So water is represented by AQ, which is aqueous. So NaCl is a giant ionic lattice. It's got lots of sodium ions and negative Cl ions all strongly attracted to each other, and they're forming a tiny crystal. So I mean, that's your normal table salt crystals. So you've got Na plus 1 and Cl minus 1 all attracted to each other. But when you start stirring it vigorously with a spoon in water, so these are all water molecules. So the ions, they start breaking off. So you can see ions breaking off. So there's 1 Na plus 1, Cl minus 1 ions. They're dissociating. The word that's used is dissociation. So the ions dissociate, and they eventually get scattered in water. So the ions, and they get completely surrounded by water molecules, which is why they're not able to form the crystal back again. Which is why when you dissolve table salt, it remains dissolved, because the ions, for example, there's this positive ion that has broken off. You're vigorously stirring it, your crystal is breaking apart. The positive and negative ions are all getting scattered. So what's going to happen is, and the way you're going to write it is that you're going to write it in dissociated form, that the Na plus 1 is now separate from the Cl minus 1 ions. So you're going to write them separately. So whenever something has dissociated, or it's an aqueous state, its ions would get scattered in water and they'll dissociate. So this is known as dissociation. So ionic compounds, they scatter into ions in water, and they're all freely roaming around. They are free moving ions in the solution once the crystal dissolves. Now coming back to the table, there's another thing that has to be memorized. So you have to memorize this. All of it. You should know which of your salts are soluble, which are going to mix in water, and which ones are not going to mix in water. So for example, the first one, here's a list of soluble salts and here's a list of insoluble salts. So first one is group 1 salts. All group 1 salts are pretty much soluble. So for example, if you take NaCl, that's a group 1 compound. NaCl is going to be soluble. So if you mix it in water, it will dissolve and its ions are going to get scattered in water. And the state that you're going to write is aqueous state. So NaCl is soluble. Any other group 1 compound, potassium carbonate, K plus 1, CO3 minus 2. So it's going to be K2CO3. That is also going to be soluble. So all of them are going to be written in aqueous state. They're going to be soluble. Any salt that's belonging to group 1, they're all soluble. Second thing, all nitrates are soluble. So whenever you see a nitrate anywhere, that's going to be soluble. So if I see magnesium nitrate, Mg plus 2, NO3 is minus 1. So it's going to be Mg, NO3 twice. That is also going to be soluble. It's going to mix in water and its ions are going to dissociate and get scattered. And one thing that you should know is that which salts are soluble, whose ionic lattices are usually not very strong. If the ionic lattice and the force of attraction between the positive and negative ions is weak, then it's easier for the salt to dissolve. And the ions, you stir it with a spoon and the ions are going to get scattered. If the ionic lattice is very strong, if the positive and negative ions attract each other very strongly, then they're not going to get scattered in water, they're not going to dissolve. For example, magnesium oxide has a very strong lattice, so it never dissolves. So also make sure you keep this in mind that solubility depends on the strength of the lattice as well to an extent. But as far as the paper or exam goes, just remember, you have to remember this table. All ammonium salts are soluble, that's the third one. So anything that's got ammonium in it, for example, ammonium carbonate, NH4 is plus 1, CO3 is minus 2, so the formula is going to be NH4 twice, SO3, so it's also going to be soluble. So anything that's got ammonium in it. Now, when we come to sulfates, well, all of them are soluble, but they are exceptions, except these ones which are insoluble. So, for example, if I have FeSO4, well, that is soluble because all sulfates are soluble. If I have BaSO4, well, that one is not going to be soluble. It's going to remain a solid. It's not going to dissolve because all sulfates were soluble except for these ones. BaSO4 was not soluble. So make sure all the other sulfates are soluble. Any other sulfate, wherever you see sulfate in the formula, that's going to be soluble, except for the ones over here that are appearing over here. Then you've got chlorides, bromides, iodides. Pretty much all of them are soluble, except for where if they contain Ag plus 1, Pb plus 2, or Hg plus 2. So for example, if I have MgCl2, Mg plus 2, Cl minus 1, so that's MgCl2, well, that's soluble. All chlorides, bromides, if I have potassium iodide, K plus 1, I minus 1, well, that's going to be soluble as well. But if I have silver, Ag plus 1, and iodine is minus 1, so AgI, then that's not going to be soluble because the table clearly mentions that all chlorides, bromides, iodide salts are soluble, except for these ones. These are not going to be soluble. So Ag, if it has Ag in it, it's not going to be soluble. Well, moving on about carbonates. Well, most of them are not soluble. All carbonates are not soluble, except for group 1 in ammonium, which we already discussed earlier on. So any carbonate that you see, it's not going to be soluble. FeCO3, definitely not soluble. MgCO3, again, it's not going to dissolve, it's not going to get scattered. But if it's a group 1 carbonate like potassium carbonate, K plus 1 CO3 minus 2, K2CO3, well, the group 1 is going to be soluble. That's the exception. Same applies to phosphates as well. If you have phosphates, if you have a group 1 phosphate, potassium phosphate, K3PO4, K plus 1, PO4 minus 3, well, group 1 is going to be soluble. But if you have any other phosphate like calcium phosphate, Ca plus 2, PO4 minus 3, so it's going to be Ca3PO4 twice, well, that's not going to be soluble. So carbonates and phosphates are not soluble, except for group 1 in ammonium. And about oxides and hydroxides, we've discussed earlier that pretty much all of them are not soluble, except for group 1 and the ones that appear lower down in group 2. So apart from these, the rest are pretty much insoluble. Like if I have copper hydroxide, Cu plus 2 OH minus 1, so COH twice, not soluble. But if I have NaOH, group 1 is going to be soluble. That's going to be soluble. So make sure that you remember or memorize the solubility table by heart and you know which ones are soluble and which ones are not soluble. The next thing that we're going to talk about is preparation of salts. And this is more to do with the laboratory preparation of salts. We've already studied a lot of reactions in which salts get produced. And some of those reactions are that you have a metal plus acid reaction that produces salt plus H2 gas. We did a lot of practice for that. There's a metal oxide or hydroxide reaction with acid that produces salt plus water molecule, so that also produces salt. Then you've got another reaction in which metal carbonate, reaction number 3, a metal carbonate would react with an acid, produces salt, water, and carbon dioxide. We did that. We did a number of equations. And the last one is if you want to produce an ammonium salt, that's going to be aqueous ammonia reacting with an acid, and it would produce an ammonium salt. Now, there are three methods of salt preparation, excess, titration, and ionic precipitation, which I'm going to come back just very, very shortly. But before that, we're gonna just go through the reactions once more. So the first thing is you have to decide what reaction is going to produce a particular salt. So here's an example. I want to prepare NaCl. That's my salt. So what reactions are going to prepare that? So we just did cover all those reactions. So remember, if I want to prepare NaCl, there should be a reaction, and that reaction. So that reaction is three reactions. Either I can go with metal plus acid. So if I want to prepare NaCl, what metal should I use? That's going to be sodium metal, and I'm going to react it with what acid? Now it's very easy to figure out the acid because it's in the formula. It's got Cl in it. So which acid has Cl in it? That's going to be HCl. That's going to be HCl. So metal plus acid would produce NaCl, and it will also produce H2 gas to go with it. But remember, the metal plus acid reaction has certain limitations that you can only use mazet metals, which are magnesium, aluminum, zinc, iron, and tin. So only these metals are to be used. Why do you need to use only these metals? Because sodium is going to have an explosive reaction. So you will get NaCl, you will get a reaction, but the reaction is going to be highly explosive, and it would be impossible to carry this reaction in the laboratory. So remember, this reaction for preparation of NaCl is not going to be used because it's going to be too explosive. Na is too reactive. So only use metal plus acid reaction for these particular metals. So what other reactions can be used to produce NaCl? We had a metal oxide or a hydroxide reaction. So the metal oxide or hydroxide in this case is going to be NaOH because it's obvious that you've got Na. So the metal is going to be Na, and hydroxide is OH minus 1. So Na plus 1, OH minus 1. That's going to be my metal hydroxide. And again, metal oxide or hydroxide reacting with an acid, that's going to be HCl again because NaCl is going to be produced with HCl. So when it's a metal oxide reacting with an acid, it's going to produce salt, plus the byproduct that's going to be produced is going to be water molecules. So metal oxide, hydroxide with an acid produces salt and H2O. Now you've got another reaction that produces NaCl as well, and that's a metal carbonate. Now again, the metal carbonate is going to be, in our case, it's going to be what? It's going to be sodium carbonate because that's the metal that we have. So it's going to be sodium carbonate, Na2CO3. Sodium is plus 1, CO3 is minus 2. And that's going to react with HCl because NaCl, the acid used will be HCl. And it's going to produce salt. And it's going to produce water. And it will produce carbon dioxide. And we can balance this equation. There's going to be 2 NaCls. And there's going to be 2 HCls. And now we've got a balanced equation. We didn't balance the first equation as well. H2, so there is going to be the first equation 2 HCls, and that would make it 2 NaCls, and you got 2 Nas, so that you got 2 sodiums over here. So now we've got balanced equations. So this and this reaction, they all produce the salt, which is NaCl. So remember, you've got three options whenever you're given a salt, and these equations, we're at the moment only discussing soluble salts, so it's only for soluble salts at the moment. And you can pick any of these reactions to produce a salt, except for metal plus acid. Can't use any metal outside of mazet, magnesium, aluminum, zinc, iron, or tin, because the other ones would be too reactive or too unreactive. Now I'm going to do another example. Let's do another example of preparing a salt, and we're just focusing on the reactions at the moment. Now, the salt I'm going to try and prepare is magnesium nitrate. And we're going to look for reactions that will give us magnesium nitrate. Now, again, I've got three options to prepare magnesium nitrate. I either can go with metal plus acid. So the metal I'm going to choose is magnesium because it's obviously magnesium nitrate I'm trying to make, and the acid, metal plus acid. The acid, by looking at the formula, you should know that that's nitric acid. It's going to be HNO3. So it's pretty obvious because it's got an NO3. So you're going to use nitric acid. So metal plus acid will produce salt, plus the byproduct that's going to be produced is going to be H2 gas. Uh, the other options, I can go with a metal oxide or a hydroxide. So in this case, it's going to be magnesium oxide or hydroxide. Let's go with hydroxide. Mg is +2, OH is -1, so it's going to be MgOH twice. And the acid I'm going to use is going to be nitric acid again because I'm trying to prepare magnesium nitrate. Now, in this case, the byproduct that's going to be produced is going to be water. It's going to be H2O. Or I can go with the third reaction, which is a carbonate. I can go with the magnesium carbonate, metal carbonate. So Mg is +2, CO3 is -2. So it's going to be just MgCO3. The acid again is going to be nitric acid. And it's going to produce salt, and you're going to get water. And you're also going to get carbon dioxide as well. And remember, this is a soluble salt we're trying to prepare. So metal plus acid, metal oxide or hydroxide plus acid, metal carbonate plus acid, all three reactions can be used to prepare the salt. The first one even, because I told you that metal plus acid only works for mazet metals. And this one is a mazet metal, it's magnesium, right? So the reaction is going to happen at a normal pace, in a normal way, and it's not going to be too explosive. Let's do another one quickly. Let's try and prepare zinc sulfate. So what reactions am I going to pick for preparation of zinc sulfate? So again, I want to make zinc sulfate. I've got three options. One is metal plus acid, so it's going to be zinc. Plus, by looking at the salt, you should be able to figure out what the acid is. It's going to be H2SO4. So the acid that's going to be used over here in this reaction is going to be sulfuric acid. And metal plus acid will produce salt, plus the byproduct is going to be H2. It's going to be H2 gas. So that's my first reaction. And again, I can use the metal zinc because zinc is part of the mazet metals. And its reaction would happen in a normal way in the lab, so you can use zinc metal. It's not too reactive. The other reactions, what other reactions can I use to produce zinc sulfate? Metal oxide or hydroxide. So I can go with, let's say, I can go with zinc hydroxide. Zinc is +2, OH is -1, so it's going to be ZnOH twice. And I can react it with sulfuric acid. That's going to be the acid. So salt plus H2O, water is going to be produced. Or we can go with the third reaction, which is a metal carbonate, which in this case would be zinc carbonate. So we can go with zinc carbonate. Zn is +2, CO3 is -2. And make sure, remember this, that zinc is not in any particular group, but zinc is always +2. It's always +2. It's not going to be written, but remember this, zinc as an ion is always +2. The acid again, carbonate plus acid, it's going to be, the acid will again be sulfuric acid. And it's going to produce, the byproducts are going to be water and it's going to be carbon dioxide. So just a quick recap, you look at the salt and you can figure, so you look at the salt and you can figure out the reaction, metal plus acid. Just be careful with the metal plus acid reaction because you can't use all metals to do this reaction. So you're going to get three. I mean, you've got an option for zinc sulfate. You can use all three reactions to prepare this salt. You just have to pick one of them. If you want to produce magnesium nitrate, you can do that. If you want to produce NaCl, you've got three options, except for the first one, you can't use that. But the others can be used to prepare those salts. So I'm just going to go through some more examples. So let's prepare aluminum nitrate, metal plus acid. The acid will be nitric acid, obviously. And the metal that you're going to use is going to be aluminium because it's obviously you're trying to make aluminum nitrate. And the byproduct that's going to be produced is going to be H2. It's going to be H2 gas. Or you can have a metal oxide or a hydroxide. So if you go with metal oxide, it's going to be Al is +3, O is -2. So it's going to be Al2O3 plus You can have the acid is going to be nitric acid, and water is going to be produced as a byproduct. Or you can go with the third one, which is a carbonate. The carbonate in our case will be aluminium carbonate. So Al is +3, so you're going to have 3, and carbonate is -2, so Al would be 2. And you can react it with nitric acid, and the byproduct in our case will be water and carbon dioxide. Now, you might also be asked to prepare ammonium salts. For ammonium salts, there's only one reaction. For example, if you're being asked to prepare ammonium nitrate, like they're asking you to prepare ammonium NH4NO3. NH4 is +1, NO3 is -1. Now, for this, you just have one option, which is ammonia plus acid. So it's going to be ammonia reacting with the acid. By looking at the formula of the salt, you should know that's nitric acid. So it's going to be HNO3. So that's the fourth reaction that we did. So all ammonium salts are going to be prepared in this way. If I want to make ammonium sulfate, NH4 is +1, SO4 is -2. So it's going to be NH4 twice. So if I want to prepare this, I've got only one option, which is ammonia plus acid again. So it's going to be ammonia reacting with what is going to be the acid in this case. By looking at the formula, you should know that that's going to be sulfuric acid H2SO4. And you can balance accordingly. There are 2 ends on the right side, so there should be 2 over here. And the same goes for the other salts. We already did that. So just remember that all ammonium salts have this one reaction, which is going to be used to prepare them. Ammonium phosphate, that's ammonia plus phosphoric acid. Ammonium sulfate, it's going to be ammonia. So it's pretty obvious. So step number 1 is figure out the reaction, which we did. So we did a number of examples, and we figured out what possible reactions can you have which can prepare those salts. And we also did ammonium salts. And remember, we're now at the moment focusing on insoluble salts only. Now we're going to discuss and come back to what is written over here, which is the method of preparation. And again, focus on the fact that we are only focusing on soluble salts at the moment, not insoluble salts. So this is all we're doing for soluble salts. Now, there are 2 methods of preparation. One is excess method for soluble salts. That is that if the reactant is insoluble and your salt is soluble, you're going to use excess method. So if you have an insoluble. And the other one is titration. Titration is if you've got soluble reactants and the salt is also soluble, then you're going to use titration. So keep this in mind. So I'm going to discuss each equation one by one. Now, the first reaction over here, we were not using this reaction. Why? Because I told you that for metals, you can only use this one. So I'm going to start writing the states for each equation. For example, over here. So let's focus on these 2 reactions for producing NaCl. Now, if you look at the states, this tiny states, group 1 compounds, remember, according to our solubility table. So remember, you would have to remember or memorize this entire solubility table, which salts are soluble, which ones are not soluble. So group 1 salts are all soluble irrespective of them. And remember, acids are all soluble as well. Keep that in mind as well. So if I look at preparing NaCl, all of them are soluble. Acid is soluble, the group 1 compound, this is a group 1 compound, Na is group 1. So the compounds are all soluble. So what did I tell you? That if all of them are soluble, then the method that's going to be used, let's go back to the method. If you have soluble reactants and the salt you're trying to produce is also soluble, the method that's going to be used is titration. So for the first 2, so the method you're going to work with, I haven't explained what the method is. I haven't explained how to do the method in the lab. But you just have to identify first thing that you're going to use titration if you want to do this reaction in the lab. Let's move on. Let's focus on this one. Remember, magnesium is a metal and it's a solid, so that's insoluble reactant. Acids are all aqueous. NO3, remember, according to the solubility table, anything that's got NO3 in it is soluble. So that's also aqueous. And you can have a quick look at the solubility table that anything that's got nitrate in it, NO3 -1, that's going to be classified as a soluble salt. So the first one, insoluble reactant, but the salt that's being produced is soluble. Let's do the other one as well. Hydroxides, magnesium hydroxide, most hydroxides are insoluble. So this one is insoluble, except group 1 and those lower down in group 2. Nitric acid is an acid, so that's obviously aqueous. The salt has nitrate in it, so that's aqueous. And I've got water, which is going to be a liquid. So again, you've got an insoluble reactant, which is magnesium hydroxide, and the salt that's being produced is soluble. The third one, carbonates. The focus on carbonates as well. All carbonates are classified as insoluble, except for the group 1 and ammonium carbonate salts. Otherwise, most of them are insoluble. So my carbonate over here is a solid. It's not going to dissolve. Nitric acid is an acid, so it's obviously aqueous. Anything that's got NO3 in it is soluble, so that's aqueous. Water is a liquid, and carbon dioxide is a gas. Now, in all three cases, you can pick any of the reactions, and so in all three cases, you've got an insoluble reactant, and the salt that is being produced is a soluble. It's a soluble salt. So in all three cases, the method you're going to use is, what is the method? It's going to be excess method. Insoluble reactant producing a soluble salt. So excess method is going to be used. What the method is, I haven't told you. I'm just identifying how to figure out what the method that you're going to use. So we go back and we label each one of the reactions. Insoluble reactant producing a soluble salt. The method that's going to be used is going to be excess method for all three of those reactions over here. Let's move to the next one as well. And if I quickly mention the solubility of each one of them, just quickly, zinc is, remember, a solid, it's a metal. Sulfuric acid is aqueous. I've got zinc sulfate, which is also aqueous. You can have a look at the solubility table. H2 is a gas. In the next one, zinc hydroxide, that's a solid. Insoluble, sulfuric acid is aqueous. I've got zinc sulfate, which is also aqueous. And I've got water, which is a liquid. Last one, zinc carbonate. All carbonates are insoluble except for group 1. So this is insoluble. It's a solid. Sulfuric acid is aqueous. Zinc sulfate is also aqueous. We've got water, which is a liquid, and carbon dioxide, which is a gas. Now again, if you look at all the reactions that were producing zinc sulfate, what is happening is you've got an insoluble reactant in all three cases, and that's producing a soluble salt. And again, when that is the case, insoluble reactant producing a soluble salt, the method you're going to use in the lab is going to be the excess method. So for each case, again, I'm going to go and I'm going to label the methods that for them. So for them, each one, it's going to be excess method. And again, I'm just stressing again, we're not writing the method at the moment. So I'm going to do the last couple of things as well. So for aluminium nitrate, all these reactions, the reactants are insoluble. Aluminium, aluminum oxide, aluminum carbonate, according to the solubility table, they're all insoluble. So if you have an insoluble reactant producing a soluble salt, nitrates are all soluble, so soluble salt being produced, it's going to be excess method again. So I'm just going to copy this, and for each of the reactions, the way the salt is going to be produced in the lab, the method or the apparatus, etc., that you will be using for each one of these reactions is going to be excess method. And let's move to the last one, ammonium salts. We had the reactions, so I just want to figure out what method I'm going to use. Remember, ammonia is soluble. Ammonium salts and ammonia, they're all soluble. So all of them, this one is ammonia is aqueous. Nitric acid, acids are all aqueous. Ammonium nitrate, that's also aqueous. This ammonia over here is aqueous. Acid is aqueous as well. And the salt that's being produced is also aqueous. So if all of them are aqueous, what was the method that we talked about? We talked about titration. I told you that if all of them are aqueous, the reactants and the products are all aqueous, you're going to go with titration. So if you want to produce these salts, the last ones, so in both cases, the method you're going to employ is the titration method for preparing the salt. So to summarize, we have done two things right now. If they want you to make a salt like magnesium nitrate, you can figure out many reactions which are capable of producing magnesium nitrate. And you can figure out the method as well, the laboratory method, by looking at the states. So you're going to do that as well. So excess method and titration, you're going to label them. Now we're going to come and discuss what is the excess method and what is titration. So we're going to start off with the excess method first. So I'm going to explain excess method first. So excess method is producing a soluble salt from insoluble reactant. We had a lot of reactions. I'm going to copy just any random reaction. Let's copy this this magnesium reaction. So I'm going to go with the magnesium reaction. Now remember, the method is going to be a general description, and you can fit any reaction onto it as long as the conditions are met. Insoluble reactant producing a soluble salt. So you've got magnesium reacting with nitric acid, and it's going to produce magnesium nitrate, and it's going to give off H2 gas. So here's an example of a reaction of magnesium metal, which is the strip of metal that's being added to nitric acid. And this is the reaction that's going on. Now, one thing you're going to do is that when you add magnesium to nitric acid, what you're going to do is you're going to add excess magnesium. And the reason why you want to add excess magnesium, what that means is that you're going to add a lot of magnesium. You're going to keep on adding magnesium until it's in excess, more than the required amount. Now, why do you want to do that? The reason you want to do that is you want all the nitric acid over here to get used up. You want to get rid of all the nitric acid in the flask because you want to produce the salt. The salt is a soluble salt, and that salt is being produced in the solution. So, for example, magnesium nitrate salt is being produced in the solution. You don't want the salt to be contaminated by the acid, so you need to get rid of all the acid. You need to finish it. So always remember that in the excess method, when you have this situation, you always add the insoluble reactant in excess. So always remember the insoluble reactant is added in excess because you want to get rid of all the nitric acid in the solution, because the solution will contain magnesium nitrate and you just want the salt. So so how do you describe producing magnesium? And that's it. That's a simple thing. Always remember, in an excess method, you just keep the insoluble reactant in excess. Now, what is going to be your description? It's going to be a 4-mark question, and they're going to ask you to describe this entire thing. So what you're going to write is, so the first line or the first point is, you're going to add excess Mg to nitric acid. And you want to ensure the nitric acid gets used up. So how would you know that it's gotten used up? Because once the nitric acid is gone, magnesium will stop reacting because it's got nothing to react with once the nitric acid is gone. And you won't see bubbles of H2 gas forming because the reaction will stop once the nitric acid gets used up. So what I've written is, you keep adding Mg until you stop seeing bubbles. That means all the nitric acid has now gotten used up. And your solution now only contains the salt because the nitric acid has completely reacted. Or you can also write that the Mg remains undissolved. It remains unreacted. That means all the nitric acid is used up. Now, the next step is, how do you get rid of this Mg? So if it's a big piece of wire or a metal strip, you just take it out with your hand. Or if it's smaller pieces, you can filter it out. That's the next thing. So simply the next point is, you filter out the unreacted magnesium. So unreacted magnesium is taken out. Now your solution only contains magnesium nitrate. That's it. That's the only thing it's going to contain. So it will only have the soluble salt, which I'm shading over here. But it's going to be in aqueous state. So they're probably going to ask you to make pure dry crystals. Now, to make pure dry crystals, you would have to crystallize. So after, the next step would be description of the crystallization process, which is, so for crystallization, the first point is evaporate the filtrate to saturation point. And once you've done evaporation, the water evaporates, the crystals would start forming if you start cooling it gradually. The magnesium and nitrate ions will start joining up, and they will start forming a crystal. You have to do it slowly so you get big, large crystals. Once those crystals are formed, you filter out the crystals formed. And that's it. Now, one last thing is, they're going to ask you for dry crystals. So to dry them, you have to do a few extra steps. So dry crystals between filter papers, or you can put them in sunlight and the crystals would dry up. Or if you want to get rid of all the water and have anhydrous crystals without any water crystallization, you can heat it strongly in an oven as well. Now let's try and do another excess method. Remember, it's going to be exactly the same. You're going to write exactly, this is your 4-mark answer. Maybe it's a 3-mark question, 4-mark question. But that's going to be, and it could come in your ATP exam, it could come in your structured exam. So just keep this in mind. Now we're going to pick another one. So an excess method. I'm just going to pick some random equation. Let's do the carbonate reaction. I'm going to copy this, and we're going to do this reaction. So I've copied this, and it's excess method. Why? Because you've got an insoluble reactant, and that insoluble reactant is producing a soluble salt. So that's why it's going to be excess method. So remember, here's your zinc carbonate, white powder, and you've got sulfuric acid. I've taken both of them. Remember, whenever you have excess method, it's the insoluble reactant that's going to be added in excess. So what you're going to do is you're going to add zinc carbonate into the sulfuric acid, but you're going to add excess zinc carbonate into your sulfuric acid. And again, why do you want to add excess zinc carbonate? Because you want to get rid of all the acid. You want all the acid to react. So the sulfuric acid has to be completely used up because the salt that's going to be produced is a soluble salt. So that salt, a zinc sulfate, will be produced in the solution. It's going to be produced in the solution. You're going to see a lot of bubbles of carbon dioxide gas. So lots and lots of bubbling, bubbles, effervescence would be seen as soon as this reaction starts. But since your salt is getting produced, and this is the salt that you're trying to make, that's zinc sulfate. You want that salt, and you want pure salt. So what needs to happen is that all the sulfuric acid, you need to get rid of all of it. All of it must react, otherwise your salt will be contaminated by zinc sulfate. Now the description of the method is going to be an exact copy paste of what we did earlier. I'm just going to copy paste this, and what I'm going to do is I'm just going to change the name of the compounds. So that's the only thing I'm going to do. So what you're going to do is, and we're going to start changing the names now. So instead of adding excess Mg, I'm going to write I'm adding excess zinc carbonate. So I'm going to cut out Mg over here, and I'm going to replace it with zinc carbonate. And I'm adding zinc carbonate to sulfuric acid. So instead of nitric acid, I'm going to cut that out. I'm going to replace it with sulfuric acid. And I'm going to keep on adding zinc carbonate. So again, over here, instead of Mg, it's going to be zinc carbonate until no more bubbles are seen. The carbon dioxide stops getting produced. That means all the sulfuric acid has reacted. So you're going to keep on adding this white powder until the sulfuric acid is gone. Once it's gone, you won't see carbon dioxide gas bubbles. So no more bubbles are seen. Or you can say that the zinc carbonate remains undissolved. So the white powder, you add it, there's no sulfuric acid left, so the white powder would just be floating around. So the other option is that your zinc carbonate remains unreacted. Then you filter out the excess zinc carbonate that you've added. You're going to filter it out because it's no longer reacting, it's insoluble. So you filter out the excess zinc carbonate. Now, once that's gone as well, the only thing that's left is your solution of zinc sulfate that's formed. So you're going to crystallize. So evaporate the filtrate to saturation point and cool gradually and filter out crystals formed. Dry the crystals between filter papers or sunlight. And if you want really dry crystals and hydrous crystals without water, you're going to heat them in the oven. So now you can see over here that I've just replaced the wording, and I've just added zinc carbonate and sulfuric acid. So it's the exact same description. You just change the name. So that's your excess method. And always remember, you add the insoluble reactant is always added in excess. Let's do another excess method example very quickly. So you've got aluminum reacting with this is a gas. Aluminum reacting with nitric acid produces aluminum nitrate and H2. It's excess method because insoluble reactant producing a soluble salt. Remember, I told you that the insoluble reactant is to be added in excess. So this is aluminum being added to nitric acid. You want to get rid of all the nitric acid. You want to get rid of all of it in the solution so that your solution at the end only contains your salt and there's no leftover nitric acid that's going to contaminate it. So you want aluminum to be added in excess. Now again, I'm just going to copy paste everything. The excess method is going to be exactly the same. I'm just going to go here. I'm going to copy all of this, and I'm going to paste it here. It's going to be exactly the same answer. I'm going to replace or remove, for example, the previous reactants. The wordings, they remain exactly the same. So now what I'm doing is I'm adding excess aluminium 2 nitric acid, 2HNO3 aqueous. I want extra aluminium to be added over here. I'm going to keep adding aluminium until no more bubbles are seen, because no more gas gets produced. That means all the nitric acid has gotten used up and it's finished now. So, or you can say that the aluminium remains unreacted. So you still have aluminium left and the reaction has stopped. That means the nitric acid is completely used up. So your solution no longer contains nitric acid. It has all been converted into aluminum nitrate. So the excess aluminium, filter out the unreacted Al. You take it out. Now your solution is only aluminum nitrate, the soluble salt. What are you going to do? You're going to crystallize, evaporate the filtrate to saturation point and cool gradually and filter out crystals that are formed, and then dry the crystals between filter papers or sunlight and so on. Now let's do one more example. I'm going to pick another excess method example, and let's pick this one. And again remember it's also excess method. Why is it excess method? Because you've got an insoluble reactant producing a soluble salt. Now, the only thing that you're going to change over here is that the method would be exactly the same. What you're going to do is everything would be kind of the same. So we are copying this, and I'm just going to paste it over here. So everything is exactly the same. I just need to add my insoluble reactant in excess. So this has to be added in excess so that I get rid of all the acid in the solution, and my solution will only contain the salt. Then I'm going to filter out the excess insoluble reactant and I'm going to crystallize the salt. So that's exactly what we're going to do. I'm just going to change the wordings over here. So all of them. So here you can see I've changed the wording. Now this is a hydroxide reacting with acid to produce salt and water. Remember one thing, make sure you correct this, that in this reaction there are no bubbles being produced. So remove this line because this would be redundant. It's not needed because there are no bubbles in this reaction. So make sure you be careful about this. In all the other previous reactions, there were gases being produced, like carbon dioxide in the previous one. So there were bubbles being produced, but not in this case. So you won't see bubbles being formed in this particular reaction. So make sure you get rid of that in your answer. So keep adding MgOH2 and until MgOH2 remains undissolved. You add too much of it that it stops dissolving. That's it. And one thing about hydroxide reactions is also remember to warm the mixture. So warm or heat the solution. Because oxides, hydroxides reactions are normally slower. So you need to sort of increase the temperature so that the reaction happens at a much faster pace as well. So you would have to warm the reactions. Carbonates and metals like magic metals, they normally react at a very moderate speed. So you don't need to heat the reaction in that case. But in this case, hydroxides, oxides, the mixture has to be heated as well. Now let's start discussing the second method of salt preparation. And that's specifically titration. And titration is going to be used when you have soluble reactant and a soluble salt as well. So we've got a number of reactions for producing soluble salts, and we're going to go and have a look at them. So soluble reactant producing a soluble salt. So for example, over here, I've got this metal hydroxide reacting with an acid producing salt and water. So it says titration. All of them are soluble. Group 1 compounds are all soluble. So I'm going to pick this reaction. So here's I've copy pasted this. So we're producing NaCl from a base plus acid reaction producing salt and water, and all reactants and products are soluble. So I'm going to highlight the reactants first. So I've got NaOH aqueous. So that's a solution. It's soluble, reacting with HCl aqueous, and that's my other solution. Now let me first quickly explain to you why the excess method is not going to work. I've taken a beaker, and what I'm going to do is I'm going to take HCl. So let's say there's HCl dissolved in aqueous state. So these are particles of HCl, hydrochloric acid. So this is my HCl beaker. And I've another beaker which has NaOH in it. So there's this other beaker which has particles of NaOH dissolved into it, and I'm going to mix them in a beaker. So remember, I'm basically trying to explain to you why excess method is not going to work. Now, NaOH and HCl are going to react according to the equation, and they're going to produce NaCl and H2O. So your products that are going to be produced in your solution are going to be NaCl plus H2O. Now remember, you can't see the particles, you can't count them. So you're adding a beaker that contains a certain amount of HCl. You're not sure what amount because you can't see the particle. Just like if I give you a glass of sugar water, you would not be able to figure out how many sugar particles are there in that glass. So you mix them up. Now, according to the equation, NaOH and HCl react in 1:1. That means if I have 100 particles of NaOH, I should be adding 100 particles of HCl. So for example, my beaker has 100 particles of HCl, but the NaOH that I'm adding from the other side, let's say I'm adding 130 particles of NaOH. Because remember, I can't count them. So 100 particles, according to the equation 1:1, 100 particles should react with 100 particles. So 100 HCl molecules will react with 100 NaOH, but the NaOH is in excess. Now, since it's in excess, that means there's going to be leftover NaOH. So although the salt is going to get produced, NaCl and H2O are going to get produced, but what will also happen is that there's going to be some unreacted excess NaOH that's going to become part, because not all of it is going to react because you're adding too much of it. You should have added 100 NaOH. So you have mistakenly added a lot of amount. So there's NaOH that's remaining. But you can't, unlike the previous case, unlike an excess method, you could have easily filtered out the insoluble reactant. Even if you had added too much of it, you could just have picked it out because it was insoluble. You could have filtered it out. But in titration, if everything is soluble, you can't get rid of this excess NaOH. That is impossible. So your salt that is produced is always going to be contaminated because you can't take it out. It's soluble. You can't filter it out. So you're stuck with NaCl being produced, but it's contaminated with NaOH. Now, vice versa, what could have also happened is that you could have added just 70 particles of NaOH. Now, according to the equation, it's 1:1, so 70 should react with 70 HCl molecules. So in this case, you're adding too much HCl now, you're adding excess of it. So even if you add excess HCl, so that means once the salt is produced, your solution is going to be contaminated by excess HCl. And since it's going to be contaminated by excess HCl, that means and HCl is also a solution, so you can't remove the excess HCl. So that's another problem, and you can't get rid of that excess HCl. So excess method will not work. It used to work for insoluble reactants because you can always remove an insoluble reactant. Will not work for soluble reactants. So what needs to happen is that. So what we're going to do is in this case, when all the reactants are soluble, if you have 70 NaOH, you need to add exactly the same amount of HCl. So you need to add 70 HCl so that nothing is in excess. So that both the reactants, they get completely used up. 70 HCl will react with 70 NaOH and they're going to produce 70 molecules of NaCl and H2O. So there's not going to be any leftover stuff, any leftover reactants that's left. So you can't use the excess method. So now coming back to our main point, which is how do you ensure that the NaOH and HCl react in exactly the same amount and you don't add anything that's in excess? Because it's going to be very hard because you can't see how many particles of NaOH there are because they're colorless. You can't really count them. You can't count the particles of HCl in this solution as well because you can't see them. So you will never know how many particles of HCl and how many particles of NaOH you've got in reality. But you have to somehow ensure that they are added in exactly the same amount and none of the reactants are in excess. Now, to achieve that HCl and NaOH react in equal amounts, you use a titration apparatus which contains a burette, which is a long cylindrical device which has a tap at the bottom. The actual picture of a burette looks like this. So this here is an actual picture of a burette. You've got a tap at the bottom. You're going to fill it up and it's got several markings over here. Normally it's either 25 centimeter cube burette or more commonly it's a 50 centimeter cube burette, which that's the maximum capacity for a burette. And the good thing about a burette is that the burette and the tap is helpful when you're not sure what amount of reagent has to be added into the conical flask. Now, coming back to our reaction, you have two reactants. One is NaOH and the other one is HCl. What you're going to do is you're going to put one of them in the burette and the other one in the conical flask. It doesn't matter which one. It could work either way. So I'm going to pick NaOH and I'm going to add it into the burette. So my burette right now has sodium hydroxide and it's filled till the top. So the burette has been filled with NaOH and I'm going to take some HCl. Normally it's 25 cm cube that's taken. And I'm going to fill my flask with hydrochloric acid, HCl. The standard practice is that you add 25 centimeter cube of HCl. Now remember, I want to produce NaCl, so the two need to react. Now let's assume that there are 50 particles of HCl over here in the flask. Just an assumption. I'm not sure how many, but let's assume that I've got 50 particles of HCl in the flask at the bottom. So what I exactly want to do is I'm going to take NaOH, I'm going to turn the tap on, and NaOH will fall drop by drop into the conical flask. So from the top, I need to ensure that 50 particles, they fall into the flask and they react with HCl. This is what I'm going to do. But when I'm doing this in the lab, I'm seeing a colorless solution falling into a colorless solution. I can't really count the particles. So what is going to happen is that as soon as one drop of NaOH reacts with HCl, the HCl will start turning into a salt. It will produce NaCl. According to the reaction above, according to the equation that's given above, NaCl and H2O is going to be produced. So as soon as your NaOH reacts with HCl, you get salt and water. So you've got 50 particles. Slowly, one by one, the HCl is going to get used up, and there would come a point when every last particle of HCl has been used up, all the 50 particles, because you've added 50 particles from NaOH at the top. So slowly, one by one, all the HCl particles will eventually get converted into NaCl and H2O. And when that happens, that's the point when I should stop. That's the point when I should stop adding NaOH from the top. But what if I don't stop and the particles, they just keep falling, excess NaOH keeps falling. So let's say I don't add 50 particles, I continue to add particles. Now there's 60, now there's no HCl left, so there's nothing to react with. So now I've got, if I don't stop there, so I'm going to get excess NaOH. So my salt, which has been formed, NaCl and H2O, will eventually get contaminated by excess NaOH. So I need to stop here. That's a must. So I should turn the tap off. But the problem is, how would I know when to stop? Because I can't see anything. I only see colorless solutions falling into it. Now, one way to decide how to stop here is that if you look at the flask, the pH of the flask would slowly change. What will happen is that initially the flask had HCl in it, 50 particles of HCl. So that would make the solution highly acidic. So the pH would be, let's say, let's call it pH 1. Slowly, when the HCl particles one by one, the NaOH falls into it, they react and they turn into NaCl and H2O. They start getting used up, and eventually there would come a point when all the HCl particles have turned into NaCl and H2O. That is when the pH will turn neutral. It's going to be neutral because a salt has been produced, and the pH would be 7. It would no longer be acidic because all the acid has been used up. But if you don't stop over here, and you continue to add the base NaOH from the top, then your solution will eventually start turning. It will start turning basic. And if you have excess NaOH, then the pH of the solution would be very basic. So it's a strong base. So let's say the pH is now 13. So the pH values would kind of indicate that at what point you should stop. So pH 1, acidic, so that means there's acid still left. As soon as it becomes neutral, that means all the acid is gone. If you add excess NaOH, that means you're going to basic. So that's when you should. So that means you basically added excess NaOH. So this is the point where you should stop. So how do you figure out the pH values of the solution? Because the pH value is going to identify when to stop. Now the first indicator I can use is methyl orange. Now what methyl orange would do is that if you add a few drops of methyl orange over here, methyl orange in acidic conditions, if there's HCl, it's going to be red, orange, or red in color. And once the solution turns even very slightly, or you add one extra drop of NaOH into the flask, then all of a sudden, under alkaline conditions or basic conditions, it's going to turn red orange or yellow orange. So as soon as this color change happens, that means you should stop. So it's going to turn red because as if HCl is present, once the last particles of HCl are used up and you add excess NaOH, that's when it's going to turn this. So that's when you immediately stop when you see this color change happening. Now, the other indicator that works very well in describing the pH values is phenolphthalein. Now, remember, these are the two more popular indicators. There are several other indicators that can also be used. But for these, you need to remember the color change. So, phenolphthalein would be colorless and acidic. So, if you add a few drops of phenolphthalein over here, if there's acid over here, it's going to be colorless. Once the acid gets neutralized and you add just one tiny extra drop of NaOH, it will become basic and it will give you a pink color. That would indicate you should stop here now. So just remember by heart these two indicators, methyl orange and phenolphthalein. The color changes are extremely important because that's what's going to happen in titration, because they're the ones that are going to tell you when to stop your titration. So just a very quick recap about everything. What you're going to do is when all the reactants are soluble, you have to add them in equal amounts. You can't add them in excess, because if you add them in excess, you can't you can't filter the excess reactant out of it. Now, so what you do is you add NaOH and HCl in the flask, or the other way around. You start adding NaOH from the top, drop by drop, and the HCl starts getting used up. Eventually, the NaOH and HCl, all the last particles of HCl are going to react and they're going to form salt and water. That's when you should stop. If you don't stop, you're adding extra NaOH, so the solution will become too basic if you add extra NaOH. So you should stop over here. And if you add a bunch of indicators or just a few drops of indicator, either one of them or any other, there are lots and lots of other indicators as well. So if you add either one of these indicators, for example, methyl orange, so the color of the flask initially is acidic, so it's going to be red orange. And as soon as you have neutralized all the acid and you have added one tiny extra drop of NaOH, it's going to turn yellow, and that's when you should stop. That would mean now you're adding too much. So stop immediately. So that's when you're going to stop. And now you've managed to produce NaCl and H2O without contaminating your salt by any of the excess reactants. And you would just have to crystallize it. You would just have to get rid of the water that's produced. So you would have to crystallize at the end. So I'm going to write a description. And remember, this description will be used for all titrations. Everything is exactly the same. So we're going to start writing the description for titration. So here you can now see I've written down the description, which is always going to be kind of the same. So what you did, fill the burette with NaOH, that's the first line. Then what we did was pipette 25 cm3 of HCl into conical flask. So using a pipette, remember that you'll be using a pipette to transfer a certain amount of HCl. Sometimes it's 25 cm3. Most of the time it's going to be 25 cm3 into the flask over here. And then you're going to add a few drops of indicator. It's up to you. You can use methyl orange or phenolphthalein or any of the other indicators. You can even get away with by just writing indicator. That's it. You don't have to be specific in your answer. So add a few drops of methyl orange indicator. We are adding methyl orange. So initially the color, because it's an acid, it's going to be red orange in color. You're going to start the titration and add NaOH drop by drop. So from the top, the NaOH, you're going to open the burette, NaOH would fall, and the HCl will get neutralized and it will slowly turn into NaCl and H2O. That's what you're looking for. So start the titration and add NaOH dropwise slowly. And you stop titration as soon as the color changes from red orange to yellow. So as soon as the salt and water is produced and all the HCl gets used up, and you add one tiny bit of NaOH in excess, it will immediately turn yellow. So stop titration when the color changes from red orange to yellow. Now you've got NaCl and H2O. Now, the only thing it's contaminated with is the indicator itself. So you add charcoal to remove indicator. So charcoal will absorb the indicator that's in the solution, so it will remove the impurity. So indicator itself is an impurity that has to be removed. There are two ways of doing that. You can add charcoal to remove the indicator, or the other thing that can be done is that once you note down the volumes that are being used, you can just repeat the whole process, but this time don't use an indicator because you know how much NaOH has to be added. So once you know the quantity of the liquids that are being mixed, you can just repeat the experiment and note down the volumes and just use the same quantities but without the indicator. But indicator removal is easy using charcoal. You can just write that. Now you've got NaCl and H2O, so the only thing left is crystallization. So what you do is evaporate the solution till its saturation point. You cool gradually, you obtain crystals, and you filter the crystals and then dry them between filter papers or sunlight. And if you need really dry crystals like anhydrous crystals, you're going to use an oven for strong heating. So that's kind of it. That's titration. And you're going to use the same exact answer for all titration explanations. So I'm going to go and have a look at another reaction. For example, we did several reactions that had titration, even the end ones over here. So I'm going to pick this one. If all my reactants and products are soluble, the method that is going to be used is titration. So let's do this next one. So all of them are aqueous. So we are definitely going to use titration. And that's what I'm going to do. So I've got my two reactants. I've got ammonia and nitric acid that needs to be they need to react. Now I can add aqueous ammonia to the burette, and the nitric acid could become part. So I can add the nitric acid below this. I'm going to add an indicator. Ammonia, remember, is basic, so that's a base, a weak base, but it's a base, it's an alkali, and nitric acid is obviously your acidic. So initially your solution is acidic, highly acidic. You start adding ammonia from the top. So dropwise, ammonia starts falling into the nitric acid, and your nitric acid will start turning into ammonium nitrate according to the equation. So it's going to start turning into, which is a neutral salt to an extent. So your acidic, which was acidic, I mean, because it's obviously an acid, is going to turn into a salt. So the solution would start turning neutral. And as soon as all the particles of nitric acid over here, they react and they get used up, it's no longer going to be acidic. It's going to turn neutral. So ammonia keeps on adding, nitric acid continues to get used up. Eventually, all of it turns into this and it becomes neutral. And if you still add excess ammonia, then which you should not. So if you still add excess ammonia, then that ammonia will not react with anything, and there's going to be excess ammonia, and your solution will now turn basic. So your indicators will change color as soon as that happens. So you're going to stop over here as soon as the color changes. In acidic methyl orange, it's going to be red, and in basic conditions, it's going to be yellow. So as soon as the color changes, that means you stop. That's where you should have stopped. So we're going to write the explanation for this. The explanation would be an exact copy paste of what we wrote earlier. So it's going to be the same exact explanation. So we're just going to copy paste the previous explanation and just paste it here, and I'm just going to change the names. The names that need to be changed is, let's say we are using the same indicator. So instead of NaOH, I'm filling the burette with what? I'm filling it with ammonia. And instead of HCl, I have nitric acid in my flask, so I'm going to remove HCl. I'm going to replace it with nitric acid. So that's getting replaced. With HNO3. And you add a few drops of methyl orange indicator. So let's just keep that indicator and start titration and add NaOH dropwise. We are adding ammonia dropwise, so I'm going to change that. So it's going to be ammonia being added dropwise. Start the titration when color changes from stop titration when color changes from red orange to yellow, which is going to be the case because methyl orange is going to be red in acidic. And as soon as one tiny drop of ammonia goes in excess, that means it's going to turn basic and yellow. And add charcoal to remove the indicator, evaporate the solution. Once the ammonium nitrate is formed, this ammonium nitrate has to be crystallized because it's also a soluble salt. So you need to crystallize this, evaporate the solution till saturation point, and cool gradually to obtain crystals. And you filter the crystals and dry them in filter paper or sunlight. And again, if you want extremely dry crystals, anhydrous, you use an oven to heat them. Now here we have another example of titration, which I've solved everything for you. So we have a reaction, potassium carbonate reacting with acid producing potassium nitrate, water and carbon dioxide. So I want to produce this particular salt. potassium nitrate. So I've taken the carbonate plus acid reaction producing salt, water, and carbon dioxide. All of them are soluble. Reactants are soluble. The salt produced is also soluble. So that's why it's going to be titration reaction. The method of preparation is going to be titration. I take one of my reactant, nitric acid, put it in the burette. The other one, potassium carbonate, I put it in the flask, and I start adding nitric acid dropwise. So as soon as the two start reacting, the potassium carbonate at the bottom in the flask is eventually going to get used up, and it will start turning into potassium nitrate, water, and carbon dioxide. Once the last particle, and remember, carbonates are basic, so initially the solution is weakly basic. So it is basic, and then it will form the salt, which is going to be neutral. It's going to be a neutral salt. And once all the basic potassium carbonate has been used up, it will turn into the products and it will be neutral. That's when I should stop adding nitric acid, because if I don't stop, I add excess nitric acid, then my solution will turn, it's going to turn acidic, which I don't want to do. So my indicators would immediately change colors. The few indicators, a small few drops of indicator that I've added. So for example, if I've added phenolphthalein in basic is going to be pink. And in acidic conditions, it's going to go colorless. So as soon, remember, indicator colors were, I've already mentioned indicator colors. Phenolphthalein in acid is going to be colorless, and in basic conditions, it's going to be pink. So remember the colors of your indicators. So going back to our question, this was the question. So I need to stop here. So as soon as I see this color change, I'm going to stop. Now I've already, remember, it's going to be the same exact description which is going to be written every time. So fill the burette with nitric acid, we did that. Prepare 25 cm cube of K2CO3 into conical flask, we did that. Add a few drops of, we're adding methyl orange indicator over here, which I can change. So I've changed that to phenolphthalein. So my color change would also change. It's going to go from pink, and one extra drop of nitric acid is going to go colorless. That's when you're going to stop. So pink to colorless. So I need to change the color change that's happening, which in our case is going to be from pink to colorless. Then the indicator is going to be removed by adding a charcoal. That's going to remove the indicator, and you're going to evaporate the solution till saturation point. Cool gradually. Once your salt is produced, just crystallize it. Cool gradually to obtain crystals, and filter crystals and dry them in filter papers. So make sure you remember this description. It could be a 6-mark ADP question. It could be a 3-4 mark question in your structured paper. So remember, this is extremely important. Now the very last method in salt preparation, that's forming insoluble salts. Now this last method is your ionic precipitation. And remember one thing, don't mix it with the previous methods that we have discussed. This is completely separate from the other two. So remember, preparing insoluble salts, these ones over here, that's going to be a totally different way of preparing salts compared to the other two. We did the first two, but not this one. And what's important is you should know the solubility table by heart. Which salts are insoluble? A lot of sulfates are insoluble. Some chlorides are insoluble, like silver, lead, mercury. The iodides, chlorides, bromides are insoluble. Carbonates and phosphates are mostly insoluble, except for these ones. And you've got your oxides and hydroxides. Most of them are also insoluble, except for group 1 and some of them in group 2. And when we are discussing this, even the reactions are going to be different as well. For this, the reactions are going to be different. So let's start with this. So one thing is that the insoluble salt is going to be produced by soluble reactants. So the reactants that you're going to choose are going to be soluble reactants. So I'm going to pick one random salt, like which is insoluble. So let's pick barium sulfate. Remember, all sulfates are soluble except for lead, barium, strontium, and calcium. So barium sulfate is insoluble. It's going to be a solid. It's not going to mix in water. It's not going to be aqueous. Now, one thing that you're going to do is, the first thing is, you're going to find two reactants. Now, barium sulfate consists of 2 ions. So what you're going to do is, this is how the reaction is going to be written. What you're going to do is, you're going to find a reactant that contains barium ions. Barium is group 2, so it's +2. And you're going to find another reactant which contains sulfate SO4 minus 2 ions. And they have to be soluble. So they have to be aqueous. So this is what you're looking for. Now, barium is not going to exist alone. It's going to be a compound. It's going to have a negative ion as well. So you've got plenty of options, which are, you need a compound that contains barium ions and it should be soluble. So there are plenty of options. Barium chloride, barium is plus 2, Cl is minus 1. So it's going to be BaCl2. You can have barium nitrate. Barium is plus 2, NO3 is minus 1. So it's going to be BaNO3 twice. What else? You can also go with barium hydroxide because that's also soluble. Barium is plus 2, OH is minus 1, so BaOH twice. These are the only ones that I found are soluble because nitrates are all soluble. Barium carbonate is going to be insoluble. Barium phosphate carbonates and phosphates are insoluble, so you're not going to use them. You have to find soluble reactants. And the other reactant has to be a sulfate. It should contain sulfate. Again, you've got plenty of options. Group 1 sulfates are soluble, so Na plus 1 and SO4 minus 2. So it's going to be Na2SO4. We can have potassium sulfate. A lot of sulfates are actually soluble. So there's a lot of options. Potassium is K plus 1. SO4 is minus 2. So it's going to be K2SO4. We can have magnesium sulfate. That's Mg is plus 2. SO4 is minus 2. So that also happens to be soluble. We can have ammonium sulfate. Ammonium is plus 1. SO4 is minus 2. So it's going to be NH4 twice. SO4. We can even go with sulfuric acid because that also has, it's H plus 1 and SO4 minus 2, so it's H2 SO4. So plenty of examples which we can go with. So I've written it over here. I'm going to find soluble reactants. I want to make barium sulfate. Find reactants that contain barium ions and sulfate ions, but they have to be soluble. So what I'm going to do is I'm going to go with one of them. I'm just going to pick barium chloride and I'm going to pick sodium sulfate. So I'm going to go with these two reactants. So I'm going to replace these two over here with barium chloride, and the other reactant is sodium sulfate. And remember, both of them are soluble. So this is aqueous and this also happens to be aqueous. And what I'm going to do is I'm going to mix them together. So I'm going to mix them together in the beaker. Now, one thing about soluble substances is that when you dissolve an ionic compound in water, the ions dissociate. So if barium chloride is aqueous, that means the crystal, all the ions in the crystal have dissociated. So they're all just randomly floating about. So your barium ions and your Cl ions are randomly floating around. Same happens to sodium sulfate as well. The crystal will dissociate in water. It's going to mix in water. So the sodium ions and your sulfate ions are all randomly floating. They're randomly floating around. Now, once you mix them, the ions are all going to mix up. And what is now going to happen is, remember, barium sulfate is insoluble. So what is now going to happen is that the positive and negative ions are going to randomly combine with each other. So if the barium ions, they combine with sulfate ions, and this barium ion over here combines with sulfate ions, they are going to form something that's insoluble. They're going to form an insoluble crystal. So the barium ions and sulfate ions will get together and they would eventually form crystals that would eventually settle at the bottom. But those crystals will not dissolve. So they would form a solid crystal which is going to be insoluble. So all the barium ions and sulfate ions that are part of the solution, they'll eventually end up as barium sulfate solid, and they would form a precipitate. That's where the word precipitation comes from. So they'll form a solid precipitate, or PPT. And what's left in your solution is Na and Cl. Now, if Na and Cl, even if they combine, remember NaCl is highly soluble. So NaCl will again mix with water and it will remain part of the solution. So the other compound that's produced is NaCl. But the NaCl never forms a precipitate because it's soluble, it's highly soluble, so it's going to remain aqueous. And that's it. So that's your reaction. So again, just a quick recap. How to write an ionic precipitation reaction. They give you an insoluble salt. You try and figure out two compounds, one containing barium ions and the other one containing sulfate ions. Both compounds, they got to be soluble. If they are soluble, you mix them, the ions will all scatter and dissociate. And the ions of barium ions and sulfate ions would combine, and eventually they would get together to form barium sulfate crystals, which will be insoluble crystals. So they're going to settle at the bottom, and whatever is left, they would remain part of the solution because that's very soluble. So that's it. And the method of preparation is pretty simple because you just have to describe what has just happened. So here I've written down the description. So what you're going to do is just mix barium chloride with sodium sulfate, aqueous. That's what you're exactly doing. And filter the crystal as soon as barium sulfate crystals are formed. You just filter them out. And since the crystals are insoluble, you can wash them with distilled water and then dry them between filter papers. Now let's do another ionic precipitation for preparing insoluble salts. Let's try and prepare AgCl. So AgCl, remember, is insoluble. So that's a solid. So what did I just tell you? When I'm preparing AgCl, I need to find two reactants. So one of them should have Ag plus one ions, and always remember Ag is plus one, and the other should have Cl minus one ions. So, but they have to be soluble. They have to be soluble compounds. Now remember, nitrates are very soluble. So what I can go with is I can go with AgNO3. A positive ion will always have a negative ion. Nitrates are all soluble. So I can go with AgNO3. Now I need another compound that has Cl minus one ions, but it's got to be soluble as well. So I can go with NaCl. Let's go with NaCl. That's it. And both of these compounds are very, very soluble. So we've found our two reactants, and what I'm going to do is I'm going to just add them in a beaker. So silver nitrate. So we are adding NaCl from one side, and remember aqueous solution. That's your normal table salt, and we are adding silver nitrate from the other side. So that's AgNO3 aqueous. And as soon as you add them, what will happen is that the ions are dissociated. They are soluble, so they would dissociate into their ions. And your Ag plus and your Cl minus one ions, if they combine, they would form. So they would immediately form a precipitate. Ag and Cl, because they're insoluble, they would join together. They would form a crystal, and you'll start seeing AgCl crystals. And they're white crystals. In this case, AgCl is white in color. So they'll form a white crystal of AgCl. And they're going to form a precipitate. AgCl PPT or precipitate is going to be formed. While the remaining ions, Na and NO3, even if they combine, they're very, very soluble. Group 1 compounds and nitrates are all soluble. So they're going to remain part of the solution. So AgCl solid is going to be formed. Plus what's left in the solution is going to be NaNO3. And that would remain aqueous. And now, just the other thing, that's the simple description of the whole process. And here's your description. Just mix silver nitrate and NaCl. Filter out as soon as the crystals are formed. Filter them out, AgCl crystals. Wash the crystals with distilled water. But remember, they're insoluble crystals, so you can wash them. They're not going to dissolve in water. And you just dry the crystals between filter papers. And that's it. Now, let's try and do another insoluble salt preparation. And again, it's going to be ionic precipitation. So I've written down calcium carbonate quickly. Remember, it's just a template. Every time it's going to be the same exact thing. So calcium carbonate, you need two compounds, one containing calcium ions and the other containing carbonate, CO3 minus 2. And they have to be soluble. So I can go with, for calcium, there has to be a negative ion attached to it. So it could be anything. It could be a nitrate. It could be chloride as well. So let's go with chloride. So Cl minus 1. The formula is going to be CaCl2 plus carbonate. I need a soluble carbonate. I can go with potassium. Potassium group 1 carbonates are all soluble, so it's going to be K2CO3. So, and remember, you've got plenty of options. As long as you've got a soluble carbonate and a soluble substance that contains calcium ions. You're going to mix the two together. So calcium chloride. So I've got calcium chloride aqueous being mixed with potassium carbonate, K2CO3. And that's also aqueous. Now my solution has all these ions mixed up, and what will happen is that if my calcium ions and my carbonate ions, they combine, they would form a precipitate of calcium carbonate. So you would immediately start seeing calcium carbonate solid precipitate getting formed. And K and Cl would remain part of the solution because so K plus 1, your Cl minus 1, even if they combine, KCl group 1 compounds are soluble, so they're going to remain part of the solution. So they're not going to form a precipitate. So the other thing that's going to be formed, the byproduct is going to be KCl, and that's going to remain aqueous. And that's it. So and you can balance this equation. Now the description, just change the description, change the names. So mix, what are you mixing? Calcium chloride with potassium carbonate. So you're mixing calcium chloride with potassium carbonate, and filter out the precipitate of calcium carbonate that's formed. So calcium carbonate precipitate needs to be filtered out, and then wash the crystals and with distilled water and dry the crystals between filter papers or sunlight. Or you want to strongly heat it, put them in the oven.